And like, as you were noting in mathematics, there's often this thing where there's a sort of a naive way of seeing a problem, but you can potentially view the problem in a totally different space. And like, I'm not that familiar, but my understanding is like analytic number theory is basically just like doing like, like totally operating differently than how you might have imagined in terms of how they approach various aspects of the situation.
Quick pause. Given that we're having a quintessential San Francisco conversation about AGI, what if I told you that you could profit from your expert knowledge in artificial intelligence? Let me show you Chollet, the first regulated platform where you can trade on the outcome of real-world events. Chollet lets you bet on hundreds of markets, from politics to tech to entertainment. For example, let's bet on OpenAI achieving AGI before 2030. I mean, obviously they won't, by the way, but let's just hedge it for a laugh. It's actually fascinating just to look at the graphs of how other people have traded, because it tells you a hell of a lot of information that you might not know. Anyway, I'm investing $500, which means a potential profit of 17% on this trade if OpenAI announced that they achieve AGI before 2030. If I wanted to be more bullish, I might bet before 2026, and I'd earn a lot more money if I was correct. Now, you should trade as quickly as possible if you know something that others don't. With Chollet's app, you can trade anywhere, anytime, and the best part, it's legal in all 50 states. Now join now using my special link, and the first 500 people to join and deposit $100 will get a $20 bonus. Now, back to the interview. Yeah, because I think that's the fundamental thing. When I read a lot of stuff on this wrong about deception and stuff like that, it's all assuming that these things have intentionality, they have goals and so on.
Or will in the future, yeah.
Oh yeah. Yeah, I mean, if that's your position, then I think that's very reasonable.
Yeah, I mean, I don't think current LLMs are that well described as having cross-context. I think they don't really have cross-context goals or cross-context intentions at the moment. But I think I'm just like, I don't know, AIs are getting more powerful.
What do you mean cross-context?
Yeah, so what I mean is you can prompt an LLM like, you should do X, even if like the environment makes this hard, and it will try to some extent to do that. But that's different from saying that it's really pursuing like kind of a specific things across many different prompts, potentially prompts that tell it to do something else. And this is like, I think this is pretty different.
Oh, interesting. Okay, cool. Well, let's slowly kick off then. So Ryan, it's an honor to have you on MLST. Can you introduce yourself for the audience?
Yeah, so I'm Ryan. I work at Redwood Research, and recently, or I guess what I'm known for is getting to a quite good score on ARC-AGI using GPT4o recently.
Yes. Now, Ryan put a blog post out a couple of weeks ago, and of course we covered it in the episode that we did on ARC just now. I was very impressed. I was surprised. Could you outline your approach and what your current accuracy is?
Yeah. So I started by just trying to mess around some with GPT4o, and I was like, hey, this model is actually not that bad at recognizing the patterns in these images. And so I tried a few different things, but ended up figuring out the best approach would be get GPT4o to write code that implements the transformation rule in ARC-AGI. So in ARC-AGI, you have these pairs of images, there's an input and an output, and the goal is to produce the output for some additional input. And I basically have GPT4o write Python code that takes in an input and generates the output. And I have it do that a lot of times. So I do that for in my most recent submission about 1,000 times per each input. And then what I do is I have all these programs, and I can run the programs on all of the examples that you're given and check that they pass all these examples, pass all these test cases. And then I pick whichever program passes all the test cases and then run that one on the held out input. That produces my output, and I hope that that's right because the program was right on the other inputs, and submit that. And there's a bunch of other stuff I do to make it more performant, but that's sort of the core of the approach that I use.
Very cool. What happens if multiple programs work? Which one do you select?
Yeah, so what I do at the moment is I do a majority vote in terms of what those programs output on the held out input. So we don't actually care about what the program actually does in general. We actually only care about what it does on the inputs we need to submit. And then we of course run it on the test cases. So if we have a bunch of programs that are all agreeing on the held out input, then it's like, great, there's no issue here. They all think the same thing is true. If they disagree, then obviously one of them is wrong because there's only one correct answer. But what we can do is be like, well, if 90% of them agree on this thing and then 10% of them think it's something else, well, we'll go with the 90%. And actually, there's you can submit two two guesses on ARC-AGI. So we can actually take the top two majority votes. So we can be like, well, first we take the one that the most vote for, then we take the one the second most vote for, and so on. I think this improves performance a tiny bit. It doesn't make much of a difference, honestly, over just like a more naive strategy. Like if you just picked at random, it's just like a higher variance approximation of majority vote, basically. So.
Yeah, I'm quite interested in this concept of ambiguity because presumably there are an infinite, set of possible programs that would solve many of the
Indeed.
ARC problems. And I'm also interested in how we conceptualize the problem. So it seems like there isn't ambiguity in how we conceptualize the problem, but there is in the solution. And then when we are disambiguating out of the possible solutions, we could argue about how we might do that. So we might pick one which has the lowest complexity or the description length or the one which is most aligned to our, human priors, if you like. Do you have any thoughts on that?
Yeah, so I'm really banking a lot on the fact that the language model is not trying to cheat. So if the language model was just trying to cheat and was just trying to special case the solutions it saw and just produce exactly those, then if you'd select for a correct program, you'd just get a program that is right on those inputs and has no hope of generalizing. But in practice, the model, puts in a good try to at least some extent. And therefore, it's sort of like we're generating the program from like, I guess, as you were saying, like the prior of programs that are like a reasonable guess at what you might do given this input, and which aren't just very specific to the exact inputs you receive. Though I do see some cases where the model like overly specializes. And then once you have that program, I don't think it would help that much to like try to pick the one that's least complexity, basically because it's just too hard. Like we don't have a great notion of complexity. It might have helped to do something like ask a model, like have another model rate the program for how much it seems overfit. And then if it seems super overfit, reject it. But I think this would probably mostly just add cost without adding much benefit because now you have to have another call to the model where it reviews every single program. But yeah, in terms of the ambiguity here, I mean, it's worth noting that there's a lot of ambiguity in like program space that doesn't apply in the behavior of the program, right? So there's many, many different ways you can implement any given thing. And then in addition to that, there's also ambiguity in behavior where you have many implementations that just do different things and many implementations that do the same thing on the test cases, but different things on potentially held out values.
Yeah. So that dichotomy between program space and behavior space, that's super interesting. And how are you thinking about that? So you're kind of looking at behavior space now rather than program space. What do you think?
Yeah, I mean, I would say my approach basically doesn't really look at the programs at all and basically just looks at their behavior. So in that sense, that's true. But I am depending on like the kind of strong guarantees on in the space of programs, which are like the programs are not trying to overfit. And I wouldn't have, the approach I was using wouldn't have any chance if the programs were random. So it also needs to be the case that the programs are actually getting close to the right solution or hitting the right solution a pretty high fraction of the time.
Yeah, interesting. I mean, in your own articulation, what do you think the purpose is of the ARC challenge?
Yeah, so I think it's an interesting benchmark that shows some ways in which current LLMs are weak and which current AIs are somewhat worse. It's more dependent. So I'd say like the biggest things for ARC-AGI at the moment, from my perspective, are vision, visual reasoning, and some amount of like puzzle solving type ability, and just general reasoning in that. And there's, also I should say there's many different ways you could approach these problems, and some of the ways will depend on different skills. The way I approached it depends on the things I said, but you could potentially use approaches that don't depend on those things at all. And I think the part of it that's most interesting to me is the extent to which it captures something like, here's a specific property that current LLMs are quite bad at, or just current AI in general, though I happen to be somewhat fixated on LLMs, or I happen to think about that mostly. And it's like, I think, current language models are very good at something. So like, there's lots and lots of programs they can write quite well. But they're banking on a lot of knowledgeability. So they're banking on the fact that they have a lot of knowledge of different programs. I mean, LLMs have much more stuff memorized than any human does. They can speak every language. They can speak in codes. They can speak every programming language. but they're somewhat less good at I would say reasoning, or like quite a bit less good at reasoning than humans. I think they still have, some ability to reason, some ability to understand the situation, some ability to learn from examples they're given in context. But it's definitely a weakness right now.
Yeah, I mean, you said visual reasoning, and that's quite interesting as well, because I'm interested in how reasoning changes in different domains. I was reading that
Mhm.
paper. I think Gwen had the paper about Terence Tao growing up. I'm not sure if you've read that. And, even as a 7-year-old boy, he was kind of like a wizard at mathematics. And apparently he preferred to use analytical methods rather than, kind of spatial methods for solving a lot of problems. But, the miracle of abstraction space is that, I mean, first of all, a lot of reasoning happens inside a modality, but abstraction is about finding meta links between modalities. So, for example, identifying that gravity is the thing which links the movement of the planets, and when the apple falls from the tree, it's like, actually
Yeah.
making that link between the domains, which is interesting. But I'm also interested, I mean, by the way, I think that the ARC challenge is about knowledge. So I think Chollet specifically said that here's a knowledge gap, and reasoning is how we acquire knowledge, and
Mhm.
intelligence is the efficiency of that reasoning process. And I'm giving you a problem where you don't have the knowledge. But then there's the question of, where does the knowledge come from? So language models, they have knowledge, and abstract reasoning is about being able to find a model, and the kind of the information space or the pathway between the data you have and the model you create might be quite tenuous. So how do I efficiently find that link?
Yeah. Yeah, I mean, you said a bunch of different things, so I'm going to respond to one thing at a
Go
time.
for it.
So one thing is, yeah, I think the puzzles are most naturally solved by humans using visual reasoning. So the puzzles reasonably often will involve things like moving shapes around, rotating shapes, uh, doing like taking a subset of one grid and looking at another. And so I think for humans, it's most naturally solved visually. Now, of course, you could, as you noted, like transform it into another regime. Like maybe you could express every puzzle in terms of some like, I don't know, like DSL that is easier for some other, like for LLMs to interact with, or maybe even easier for some humans to interact with, and that doesn't actually get corresponded to visuals at all. And like as you were noting in mathematics, there's often this thing where there's a sort of a naive way of seeing a problem, but you can potentially view the problem in a totally different space. And like I'm not that familiar, but my understanding is like analytic number theory is basically just like doing like like totally operating differently than how you might have imagined in terms of how they approach various aspects of the situation. So yeah, I think I basically agree with that. My guess is that in practice, the most effective way to solve ARC-AGI puzzles, at least using the sort of approach I used, is going to bank on visual reasoning, and is going to bank on the fact that models have been trained on huge numbers of images, and over the course of that, acquire some somewhat general ability to reason about images, understand images, recognize patterns in images, even if that ability is somewhat weak. Um, yeah. So you said the just going into your next point, you said that the ARC-AGI challenge or whatever is about knowledge. It really sounded like your description was more that it was about quickly acquiring or applying knowledge, or like zooming in on that. Like for example, for any given puzzle, I don't think that anyone, assuming the puzzle is sufficiently distinct, has an existing like rule that applies to that puzzle, which they've already found in their head. Like no one has like memorized the rule from the set of like a bajillion rules and then is pulling that out. I would say it's more like, I don't know, at least for me, I've solved a decent number of these puzzles now, just messing around in this sort of stuff. And for me, I have like some sense of what the moving parts here are. Like, oh, there's this thing where like you're looking at a subset, you're changing colors. There's like various styles. There's like fill in the blank. There's grids, and I sort of have these moving parts in my head, and that makes it so I can solve these puzzles much faster. Because I've sort of overfit to the domain actually, because I've looked at a bunch of these, and I think humans definitely get better at solving these over time. I certainly I have, and and then you can move around these parts, but you can also solve them relatively de novo just using knowledge that most people have. My guess is that the way the language models are doing it, at least in my approach, is somewhere in between, where I think they're probably not actually as overfit to ARC-AGI as I am in some sense with my approach, because I think they probably have fewer examples that they're have as like good recollection of that they've learned as well from at the moment. Because while they've been probably trained on a bunch of related data, they were trained on it in addition to a bunch of other data, and they probably don't have it as salient. Whereas I spent like, a bunch of time messing around with the puzzle. That might change in the future. I don't know what the next training run for the next model looks like. But my guess is that in some sense they're actually operating from sort of a disadvantage in this regime, which is a little surprising because in most cases their advantage is having seen this. But I think in this case that's one of their disadvantages, is that they haven't actually been trained on, or like it's not as active for them.
Yeah. Well, yeah, I think there's an interesting dichotomy between System 2 creation versus System 2 intuition. So when you're solving riddles, many of my friends tell me about this, it's a skill. It's actually something you can learn. And I think of the ARC as similar to the concept of abduction, right? So, I'm basically cutting down, I'm framing a set of plausible hypotheses and I'm doing inference over those hypotheses. And this is guided by intuition. Now, when kids are taught mathematics at school, they're not allowed to use their calculator because we teach them how to reason, right? We teach them the rules, the axioms, and so on. And, you might sort of naively say, well, why bother? Just give me the calculator. Well, the reason is that these rules can be intuitively recombined and composed together to solve other problems. It's really powerful knowledge. So now we're just kind of, we have this knowledge and we're just interpolating over it. We're using our intuition and so on. But the key question is, where did the knowledge come from in the first place? So at some point, some very bright person, this is what we do with science. We come up with models, these abstract models that work in many, many situations. And then most of us don't use the models because, we already kind of know about them being used. And then we just do pattern matching and intuition over them. Mm-hmm. But at some point, the models either got invented or they got discovered. And then there's the question of, well, how fundamental are these models? So even mathematical operations can be expressed in forms of like set operations or whatever, right? So you could have like, some real fundamental operations, and we can have an algorithm that does program learning, and we have this like library of inscrutable kind of compositions of operations or whatever, and maybe that'd be good, but it wouldn't be very human aligned. It wouldn't be very understandable. But what do you think about how fundamentally we could represent knowledge and where the knowledge comes from?
Yeah, so one thing, a bit of pushback there. I think in practice, people who really are good at working with models basically do reinvent them with the inspiration. Like, I think that it's very common in my work that like I basically reinvent ideas that I had 6 months ago all the time. And I'm like, oh, that's a good idea. And I'm like, well, I basically already kind of knew that. But I think I find at least like something that's sort of like rediscovery with like hints is actually pretty key to my ability to have things in place. And like in some sense, like the best way to have compressed memory is to have the barest pointer to a thing such that you can rediscover it. And I think it's like in a lot of intellectual work, it's I forget where I think I first read this in some blog post, but like it's a good idea to be in a regime where you can basically reinvent any key piece of knowledge from the rest of your knowledge, and do that. And then as far as the claims that like ARC-AGI is about like abduction, I would say that for me at least, a lot of the puzzles I basically, or like at least a lot of the easier puzzles, I basically just use something more like intuition. At least for me, like as in what I do is I look at the puzzle and I sort of just know what the rule is, and then I'm just like, great, I know what the rule is, and then I check it. But like then I'm just right. I just knew what the rule was. And then there's some amount of puzzles where you like figure out what the shape of the rule is, but there are some free variables. Like, okay, I know that this shape is being changed color in this way, but in what way is it being changed? Like in what way is the color being changed? And I do have to do conscious, as you were saying, like sort of more system 2, like thinking slow style reasoning for that. And I agree that is in fact a core element. I think interestingly, in the setup I use, it's not like both phases happen at two different points. So there's sort of kind of two parts to my approach. One of them is that I have the language model do reasoning and generate the code. And it does sort of chain of thought reasoning that based on how I prompted it. Then it generates code. And then I do sort of selection over these programs. And I would say that there's some amount of both selection for having the right intuition and selection for having the right, like, more like system 2, trickier to pin down parts that require like testing things in the selection phase. But it's also the case that when the model does reasoning, it does do a bit of both the intuition and also some amount of eliminating hypotheses. It's not great at this. It's pretty bad. It messes it up a lot of the time, but it does in fact correct itself some of the time. And it does like, analyze the situation sort of more in a system 2 way, where I have it describe what the different grids look like and notice commonalities. And it messes it up a lot, to be clear. Like, it's not, if you looked at these reasoning traces, if you looked at the average reasoning trace, you might not be impressed, but it does have sort of I would say, a spark of the actual reasoning, of the actual ability in there. And then in addition to that, I also do a second pass, which is quite helpful, which is I take solutions where it seemed close, like it seemed like the model was kind of getting close to it, but it messed something up. And I give it to the model again in another context, and I say, hey, here's a solution that some idiot wrote. I wonder who wrote this. Can you fix it and make it so it actually works? Here's what it actually output on the examples. Here's what it was supposed to output. You should fix the code. No, I tell the model that it was a previous version of it that wrote it. But I think I don't know. I think it's sort of funny that it's like it's just getting this thing from the blue and being like, yeah, someone wrote this. Now you have to fix it. And it's just sort of appearing into the void because it doesn't really have much context, doesn't have much state, and it just has to fix this program that someone else wrote. But yeah.
Yeah. I mean, you said a few things there that made me think of three things. I mean, first of all, there's a fundamental search versus framing dichotomy. And, a lot of the early solutions just did an exhaustive search, a bit like an early chess algorithm where you do, basic alpha beta pruning or whatever. And yeah, that works, but it's not intelligent because, efficient reasoning is intelligence. And then there's the notion of, okay, so you're generating a bunch of completions and you're doing some refinements and so on. And you could argue that, I mean, imagine there's a Venn diagram of the knowledge in the language model and the knowledge in the ARC problem. And if they mostly intersect, then, in theory, there's some solution which is traversable inside the language model. So I'm not sure what you think about that. But there's also the thing about doing these reflective steps and, the chain of thought reasoning and so on. Because you can almost think of that as an agential potential set of trajectories. So if you imagine I'm setting up the chain of thought, I'm setting up the prompts, and I think of language models a bit like a database query. So what you're essentially doing is you're creating a cone of possible retrieval trajectories, and you're also eliciting external information from the evaluation function, which in this case is the Python interpreter, and you're kind of like traversing that. And it's already interesting that the solutions are so easily found. I mean, I know we're talking about 30,000 completions, but that's actually a lot lower than I thought it might be, which is quite good.
Yeah, so my most recent solution uses closer to 1,000 completions.
Oh wow, okay.
So
tell me about that.
Yeah, so for the most recent submission on the public leaderboard, I use fewer submissions per problem, basically because I wanted to run it on more problems and there was a cost budget, and I included a few minor improvements as part of that, or as part of that like resubmission. But yeah, so it does include fewer solutions. I should also note that we can look at the curve of how many solutions you use versus how well do you perform, and it's not that. It's in some sense, from some perspective, the curve is very brutal, and from some perspective, the curve is very optimistic about language model abilities because there's really not amazing returns to adding more samples. So roughly with my approach, I think it's something like each doubling of samples gets you something like maybe about 4 or 5% additional right with my most recent solution if you account for all the different steps that I'm using. And so I'm like, okay, we're exponentially growing the number of samples we're using, and we're getting a fixed return in terms of what we're solving. And it's quite brutal because if you wanted to get an additional 30% correct, you would need 10 doublings. 10 doublings is what, it's like 2,000 or something. I'm like, that's a lot of doublings. But at the same time, it is the case that means that at a small number of doublings, like at only let's say, I don't know, about 128 total completions, we're getting non-trivial performance. So I think, for example, with my with my most recent approach that I was submitting, with about 256 completions, I think I was getting about maybe around 35% accuracy or so. And now I think that's quite a bit worse than humans would do. But it's not wildly worse than what humans do. My guess is on the test set that I was evaluating, sort of a typical human performance is maybe around 70%. I don't really know. My performance is probably quite a bit higher than that, maybe. But I'm practiced. I'm probably better at solving these problems than typical people are. And maybe I get 90, 95%, and maybe a reasonable fraction of my mistakes are due to messing up, typing things into the clicking the grid or whatever. They're sort of less interesting. But it is getting something, and some of the puzzles it's getting are not that trivial, even in the case where it has this many samples. And if you look at the reasoning traces, it's pretty often that it sort of gets the idea, but it fucks something up. Like it'll get like, oh, there's like something with horizontal lines and I'm supposed to like complete them or like add more horizontal lines. And it'll be getting the idea, but then despite getting the idea, it messes up one of the details, or sometimes it gets the rule basically right, but messes up the implementation. Like it'll have done all this hard work and have just, it'll have luckily gotten onto the rule, and then it'll have an off by one error. And then it's like, no, you're so close.
Yeah.
But yeah.
Yeah, I enjoyed reading your blog about that. Yeah, it was surprising, and I've tried a few examples as well. And similarly, I was impressed by the ability of GPT4o to get the outline of the solution. But then, as you say, there's a surprising number of like just stupid little errors that shouldn't be there. But a couple of things I wanted to point out. So when I spoke with Jack, he is talking about essentially, fine-tuning and augmenting and doing so-called active inference. So he's actually retraining the base model. So what's very interesting about your solution is that you don't do that, right? So you're using a foundation model, and then you're doing a whole bunch of computation, like a pattern of computation, but freezing the base model, which is very interesting. But I wanted to talk to a little bit what the trade-offs are there. So I'm going to use the term aspect ratio to talk about the trade-off between doing lots of initial completions versus doing deep completions, which is to say doing many steps of refinement. What's the trade-off there?
Yeah, so I'll start with the aspect ratio question, then maybe I'll get back into some of the trade-offs on active inference versus something else. So as far as that, a really, really important aspect of how my solution ends up working and the choices I made is that I am really heavily using the OpenAI like end completions feature, or just like a feature that various LLM APIs have, is the ability to get out end completions where you only have to pay for the prompt once. So we'll have this language model, we'll give it a prompt, and we get out a completion. And by default, every time we get a completion, we have to pay for the model processing the entire prompt. But it turns out, because of some sort of clever details about how the transformer architecture, at least a causal transformer architecture, works, that we can actually like sort of save the prefix and just process the prefix once and get out a bunch of completions. And there's some non-trivial aspects of this, but basically there's a bunch of different like APIs and libraries support the option of being like, for a fixed prefix, we get out a bunch of completions all at once. And without this, my solution would be much, much, much more expensive, like maybe 10x more expensive. Maybe I think about 10x more expensive is about right. And so I actually don't really have the option of doing things that are very deep, because I have this huge subsidy towards branching. Because at each point, if I branch by less than a factor of about 32 or 64, I'm leaving money on the table. And like I think we should actually think of these sorts of solutions as, what is the cost per performance? And I think that's a very natural way of thinking about, especially solutions for ARC-AGI, but also solutions for other problems. And so I basically just don't even have the option of going very deep with the current technical affordances I have. That said, it's not as though it would be impossible to go deep. So I was saying before, you can cache the prefix, or you can save the processing done on the prefix. So that also can work for going deep. You can basically have the model, it generates an output, and then we now cache both the prefix and the new output it just generated. And then we sample another output, and we keep going with that, and have interaction from the world back and forth there. And I should also note that each completion from the model is both doing reasoning, and that reasoning can be as deep as the model wants, and also is generating a completion. But you might have thought a more natural workflow, especially with the solution I use, is something like, you generate a completion, you then look at what it outputs, you do debugging, maybe even let the model use tools, like you let it use tools, like it can zoom in on the grid somewhere, it can try to use some, it can click around, it can visualize things using various visualization tools you give it, where it could just write some Python code that generates a visualization. And I think all this totally could work, and there's no strong obstacle to making it sort of more like an LM agent that is sort of navigating the world and doing a bunch of actions before it eventually zooms in on a final submission. And the reason why I didn't do that is, as I was saying before, it would naively have too low of a branching factor to be efficient, and it wouldn't work that well. Another reason is that models right now are much better at sort of making a good first attempt than at debugging. I don't know if people have ever tried debugging with models, but very often they'll sort of get into loops, they'll mess things up, and they can do it. They can do a bit of debugging, especially these days. I think 3.5 Sonnet is maybe just on the basis of various benchmarks in Anthropic's sort of blog post, it's maybe better at doing sort of agentic tasks and debugging. They said they had some, pull request benchmark where it was doing quite a bit better. But it's also much better than humans at drafting working code on the first try. Like, I don't know if you've ever tried just taking a programming problem and just writing out the entire solution in one go, no backtracking. It's not easy. Like, this is not an easy thing to do. And the models are just doing it straight up. And so they're much better in some sense than us at doing that. But they're worse at the process of being like, oh, I drafted the solution, but there's this issue. I need to fix this. And people are, this is improving over time. People are training them to do this better. But for that reason, sort of the width is maybe both cheaper for the affordances I had access to, and also it's sort of the LLM specialty is sample a bunch of things, pick the best one. And I think this is a common pattern is sample the best things, or sample a bunch of things, pick the best one. Okay, so that's the sort of the depth versus, I don't know if width is the right word, aspect ratio you were saying. Question.
Yeah. So, and I was quite intrigued by what you were saying actually about, so there could be some agentic solution where an agent is actually kind of, sampling information from the grid and doing a bunch of stuff. And, essentially I can imagine some kind of a graph of computation. And we might be able to, make some statements about the efficiency of reasoning based on the shape of that graph and how much work is being done. But one thing that does come out to me is that, this is a neurosymbolic method. So that graph has heterogeneous compute, which means it has like a mix of different computation models. So it's got some LLM inference and it's got some Turing machines, it's got the Python interpreter and so on. So we're mixing a bunch of things together. And I think that's relevant because I think having that hybrid approach is important. But what do you think about that?
Yeah, so I feel like the term neurosymbolic, it feels a bit misleading in this case. I agree it applies for the reasons you said. Like, if you're going to be like, well, there's some aspect which is using the Python interpreter, therefore it's neurosymbolic. That's fine. That's a fine way to define a term. But then in that case, we should be like, great. So software engineering is a heavily neurosymbolic discipline because when I software engineer, I run code, I run linters, I am constantly looking at the outputs of programs, I'm using tools, I'm using static analysis tools, and and that's fine. We can be like, great. So a key aspect of software engineering productivity is giving access to a bunch of tools. I think it maybe gives people the wrong view of what's going on in terms of how the typical connotations of the word in this case. Because at least for me, the connotations of the word are more like a core aspect of the processing of the system in terms of how the system is doing like real, like honest to goodness thinking is in like symbolic representations that are sort of using like computer programs as opposed to learned. And I don't think that's super accurate, especially in the case of what I was doing. Now, there's a spectrum. Like, there's a question of like how much is one thing versus how much is another thing. I think my solution is it's certainly much more neurosymbolic than if the solution was just you have the model, you prompt it, it generates in one go, it outputs the completed grid as sort of just like an output in tokens. But at the same time, I think it's much less neurosymbolic than approaches you can imagine. For example, or like much less, I guess, symbolic on the neurosymbolic side than approaches you could imagine, which are more like, explicitly representing a bunch of symbolic state and doing sort of, something that's much more like where I guess more of the like structure is being built up at that level. Whereas it feels like a lot of the structure from in the case. In the approach I'm using is basically coming from the fact that the model writes code. And you can even cut the part where we do revision. You can basically just be like, the solution is just the model takes in a problem, it does some reasoning, it outputs some code, we pick the best piece of code. And then now there's like basically one symbolic component, which is, or like one-ish symbolic component, which is picking the best piece of code and then generating the corresponding thing for that piece of code. And indeed, that's an important component. It helps a lot. But it feels like it's more analogous to like there's a bunch of problems where if I was to solve them, the way I would solve them is I would write code to solve them. I wouldn't do it myself. I don't know. Yeah, sorry, pushing back there, but there's more content here. But yeah, you want to continue with?
Well, just a quick comment on that. I mean, it's not just picking the code, it's also running the code because the actual artifact that you have produced is a symbolic program. Now, I believe that to solve something like an ARC challenge, you need to have a hybrid architecture, which means you need to have a type 1 component and a type 2 component. And the interesting thing with your solution is you've gone type 1, then type 2. So you kind of, you've got the intuition bit, you generate a program, which you evaluate and select on, but you also run the program because that's the artifact. And this is what Chollet said. He said like an intelligent system is a thing which produces skill programs. And then because it is a type 2 program, it runs on a Turing machine. That means it can have an expandable memory. It can address a potentially infinite number of possible situations because these Turing machines have infinite tapes. Jack Cole said that symbolic type 2 programs are narrow but deep, and type 1 machine learning type programs are wide but shallow. So having that as an output artifact is clearly very, very robust, because if you have a well-described program in Python that does this kind of geometric manipulation on the 2D grid, it's clearly going to work in an infinite number of situations. In the same way that your Python program, your interpreter, it can accept an infinite number of possible Python programs, because it's just a different model of computation.
Yeah, so I again want to push back here a bit. So I'm like, suppose
Sure.
that a human solved ARC-AGI via first thinking about the puzzle and then writing a program to solve the problem. I think I would say they're doing system 2 reasoning when they're writing the program, not just when the program is being evaluated. And yes, they're also doing system 1 reasoning when they're doing it. They're doing both. And I would say I think it's also the case that in the approach I'm using, neither the program evaluation nor the language model cleanly maps onto purely like something well described as system 1, system 2 style reasoning, or like maybe the program evaluation maps clearly onto system 2. But it's also compensating for system 1 weaknesses. So like the way I would think about it is like the model, it takes in some programs, it has some intuition, it starts generating on the basis of that intuition. Maybe it's also doing system 2 reasoning internally. Probably it's doing very limited system 2 reasoning internally because, models are quite dumb and also they're quite shallow. But it's probably doing, I would say it's probably doing like a little bit of something that's well described as system 2 reasoning internally. And then it then starts generating, and it's generating these tokens, and these tokens are doing system 2 reasoning. So it's doing stuff like starting to outline what's going on in the grids, describing that in words, considering a few things on the basis of what it's described in words, maybe rejecting some hypotheses in some cases, or refining its guess while it's generating based on what it's seen so far. And then it generates this program. And then the program is passed off to some process. And that process is, I would say in some sense, it's compensating, like as in we're doing selection to compensate for the fact the model fails sometimes. And it's compensating both for system 1 failures and for system 2 failures. Like it's compensating for both of these. And I would also say that like in humans, there's a relatively nice system 1, system 2 divide. Like I think this is a very good model for thinking about reasoning in humans. It's not very clear to me that this will be a good model for thinking about reasoning in future systems constructed out of AIs. It might be. I don't think there's a strong reason to think it won't be. I mean, it applies in one case. Why not apply another? But I think we should be careful to avoid overfixation on one model. Though I think it doesn't seem like a terrible model in the case we're talking about right now. So
yeah, I don't think we're a million miles away from each other. I think it could be said that the LLM component is as if it's doing system 2 because it's doing a kind of interpolative form of system 2 reasoning rather than an inventive form of system 2 reasoning. And there was, we won't go into this, but there was a great paper by Fodor and Polishin in 1988 called A Critique of Connectionism. And they were just basically arguing, and this goes back to the days of Hinton, that neural networks, they don't do symbols because all of the downstream operations do not maintain the intentional structure of the computation. That's a different type of intentional. That's intentional spelt with an S, so it doesn't sort of like maintain the underlying symbolic algebra of the operations. But then again, like you can look at the output of LLMs, and they do seem to be doing symbolic stuff, right? They can do all of this symbolic manipulation, and they're quite consistent. And I think it's a bit of an illusion to think that they work in the same way. I just think that there's a huge space of kind of colloquial, interpolative, effective reasoning that looks as if it's reasoning, but there is a difference in kind.
Yeah. I think we're not that far off, but I do disagree here. I think I'm like, well, suppose that we just play the Turing we do a Turing test on our language model, and we've got one human and we've got one language model, and you're like, damn, the language model really seems like it's doing okay here. It's really doing a lot of stuff. Like maybe the reasoning is happening in chain of thought, maybe it's happening inside the language model. I'm just like, at some point, if the language model was good enough, you have to be like, well, I don't know what it's doing. I don't know if it's interpretative. I don't know if it's that. But it's accomplishing the same objectives behaviorally. It's doing the same thing. And I'm like, who am I to judge? Who am I to judge why it works? I mean, it's interesting why it works. But I think we should be careful to jump to conclusions about about like what the limiting factor is when we don't really understand these systems and we don't understand what's going on internally. My guess is that if you were to look under the hood and really understand what's going on, you would both see a huge amount of intuition, a huge amount of knowledge, and they would sort of be cheating in a bunch of tasks from this perspective, or, you know, doing them in a very unhuman-like way. But at the same time, my guess is that at the end of the day, there's a bunch of cases where they're actually doing the thing the right way, or like doing it in like a way that actually involves relatively general abilities. And it's, you know, it's narrow now. They're compensating for this, but I think it's building up over time. And I think I'm like, you know, you maybe start with like shallower heuristics, you build towards deeper heuristics and to deeper heuristics. And I'm like, system 2 reasoning is just a special case of deeper heuristics that the model might learn over a bunch of training. Now, the transformer architecture, it has some ways in which it's less well suited to this sort of reasoning, but there's no fundamental computational reason why this can't happen, right? So there's limited depth, but I don't know, a human in 5 seconds also has limited depth. And nonetheless, a human in 5 seconds can do things that are well described as a bit of system 2 reasoning. And I'm like, it seems to me like the models can often do tasks in one forward pass without doing any generation that a human would you know, take 20 seconds to do and would have to really think about. And they're probably cheating a little bit, doing a little system 2 reasoning, mixing it all up. That's one thing. The second thing is it's worth noting that models can use chain of thought. So they can do this reasoning in words that I think can, in many cases, correspond to pretty closely to how a human would do the problem. So like when models solve math problems, it seems to me like it's very similar to how a human would solve a math problem in many cases, where you're like, well, I'm gonna first add these numbers, then I'm gonna multiply by that, then I'm gonna like think about what the next step is and do that next step. And each of these steps happens one at a time, and they potentially can change course. Now, there's various ways in which the models are doing it somewhat differently. Like there's this interesting work people have looked at where they're looking at like what is causally responsible in the chain of thought. And like, you know, so like the model generates some stuff and it's like, well, first it does like 1 + 2, and then it multiplies that by 7. And you're like, suppose you just change the 7 to be 8, or, you know, you change the intermediate results actually really. So it's really, you change 1 + 2 to be from 3 to being 4, and then you keep going. How often does this mess up the model? And it turns out that at least for the biggest, most powerful models we have now, changing any intermediate value only affects it by a little bit. Doesn't butcher it, you know? You might have thought that if you change it to 4, it would always get the next number wrong. But it turns out that the model is sort of doing a bit of a sort of like more wishy-washy thing, which I think humans also do. So like, for example, if you're writing out your chain of thought, or like, you know, you're writing out your current reasoning, sometimes you'll make mistakes that you'll then not pick up on. Like, as in, you'll sometimes do 1 + 2, you'll write 4, and you'll kind of have known that you meant 3, but you made a mistake in what you're writing, or you thought the wrong thing, and then you'll sort of keep moving on. It's also possible the model sort of recognizes the error. Like it just knows really strongly that 4 is wrong, and it's like, well, there was an error there, but what's the most likely guess for the next thing? It's still the correct thing, because even though there's an error there, continuing it correctly is still more likely, and it's able to sort of compensate for the errors. Anyway, yeah.
Yeah. Well, I mean, this reminds me of, this is the beauty of connectionism, and it goes to Andre Karpathy's Software 2.0 article, where he's basically talking about this progressive, diminishment of fidelity in a neural network, and it still does the same thing, just half as well. And I agree, maybe in some modes of our cognition, we do the same thing. And this is what a lot of connectionists think. I interviewed Nick Chater, and he basically thinks that the mind is flat and it's just an inscrutable, blob of neurons, just like a neural network. And actually, all of this kind of type 2 reasoning that we think we have in terms of intentionality and consistent beliefs and so on, they're just an illusion. Actually, we're much more similar to neural networks than we think. But this does go into a couple of interesting directions, though. So I agree with you that people both overestimate and underestimate the capabilities of neural networks.
Absolutely.
In my view... Oh, yes. In my view, I like to hone in on the agency question and the reasoning question, and even the creativity question for me is the same as inventive reasoning, right? So I think that the difference is in whether people see them as tools or agents. And for me, an agent is very important, by the way. So there's a minimal agent, which is just where the cause of the behavior comes from the inside, not the outside. So like a little bacterium going up a sugar gradient is a minimal agent because, the behavior came from the inside. But obviously the strongest form of agent is an intentional agent. So it's actually a thing that sets its own goals and like it wants to shape the world around it and so on.
Yep.
And I believe that neural networks don't have the inventive reasoning or the agency, and I'll explain why. I think that there's this kind of long tail of brittleness with these models, and because they're used as tools, the humans don't notice that they're doing the reasoning. So when we do the prompt, we're actually doing the reasoning, and obviously the cause of the action and the goal came from us. And then what happens is, you do the chain of thought, and you do all of this prompting, and you create this kind of trajectory. So you can set up autonomy in the agent, and it can still follow an interesting trajectory of possible patterns, but it's convergent, right? It's not open-ended in the same way we are. And as I said, you could just argue that actually we don't have agency either. That's a separate issue. But you see what I mean? You just kind of got this fixed trajectory, and we anthropomorphize, and we misassign, like the reasoning and the agency to the models.
Yeah. Okay. So I guess one thing that's worth noting is I do think that there's structure in the brain, but it's both the case that there's structure in the brain and that there's sort of basically connectionist paradise in the brain. There's like totally uniform tissue, which is learning. From my understanding, I'm not a neuroscientist, but my understanding is that we then like people the current state of the art in neuroscience thinks that the frontal cortex is highly uniform, and in fact like a lot of the reasoning that we're most impressed by is grown out of what is basically uniform, though there's some structure imposed by recurrence, etc. And I think that's worth noting. Second of all, it's worth noting that LLMs are also not fully connected MLPs. They have structure. We designed an architecture. And in the same way that I would say the analogy I would use is like evolution designed the structure of our brain and created a bunch of uniform stuff that can like learn from experience. And in the same way, human designers and also potentially like, people have done algorithmic search for architectures, but human designers and selection on human designs have created this neural network architecture. And that neural network architecture is relatively uniform, but it's learning like throughout lifetime. So I would say like an LLM training run is sort of very similar in my mind to within lifetime learning. I'm stealing this analogy from Steve Burns, who's someone I read sometimes. And I think I'm like, they seem pretty analogous to me. Now there's a bunch of ways in which they're quite different at the moment. So for example, LLMs, I think, I forget the exact calculation, but if you imagine each token is 1 second, maybe they live for like 30 million years. I'm like, that's a fucking long lifetime. Like that's a really long lifetime if you're an LLM. I don't live for 30 million years. It's not where a lot of my action is coming from. In addition to living for 30 million years, if you start at year 30 in the LLM's life, it sucks. It totally sucks. It can't do anything. And so it really needed a huge lifetime. But at the same time, like, I think you can also imagine that it's basically sort of living each moment a little less. Like the LLMs learn less from each moment, but it's also computationally cheaper. Like current LLMs spend less compute on each token than a human spends on each second, based on our understanding of how much action the brain is doing. So they're sort of shallowly living a much longer time. And you can kind of see why this would be good. Like if you could prefer to spend as much resources on twice as much time, but live it a little more shallowly, my guess is you'd prefer that. Anyway, so this is just thinking about that and the in context question. My guess is that indeed structure helps. I think I'm just reluctant to say. So you were saying like maybe the dichotomy you were presenting is either the neural networks don't have X or humans don't have X. But I think there's an intermediate regime, which is like humans do have X, but X is learned. Like I think a bunch of the agency humans have is actually learned, and a bunch of the ability humans have to like process and manipulate symbols is actually learned. And some of it is baked into the architecture. Some of it's learned. We don't know which because we don't understand how the brain works. But it's probably some of both. And like in fact, you can learn how to manipulate symbols better, as you were noting earlier. And I think it is general. Like I think there's some stuff that's baked in, that's basically baked into the architecture, and there's some stuff that you can learn and get better at, and there's lots of things that people can acquire in terms of skills here. And I think that the language models are probably somewhat similar, where they can probably, learn how to learn, basically, where like humans can like learn processes for better like looking at stuff and then figuring out things quickly. And I think the LLMs are similar. So there's, in context learning where you have a bunch of data that you give in the context of the language model. And the language model can come away with conclusions that, I don't know, they look awfully similar to how humans would learn from text. And maybe they're different fundamentally. Maybe there's something fundamentally different going on. It's certainly possible. It's hard to rule out because we don't know what's going on. And we know we can say some things are different. So it's much shallower. So like current language models, they have much shallower reasoning. And when they're processing a long document, they're not reading through it a paragraph at a time. They're reading through all the paragraphs at the same time and then doing some mixing on top of that. So it's definitely somewhat different. But I'm like, I don't know. It seems like it has the spark of learning to me. I'm like, it really feels to me like if you were going to draw a line that was like, here's where real learning starts, that line would be crossed. And so I think I'm like, they have some learning, they have some reasoning, they just kind of suck at it. And I feel like that's a lot of my view. Now getting into the agency question, which I think is also interesting. Maybe I'll give you a second to respond to that and then I'll get into agency.
Well, no, I think the agency is actually a very interesting thing. I wanted to clarify as well that I'm not necessarily an agency realist. I think of myself more as a agency instrumentalist. Which is that it's an as-if property. Along the lines that Daniel Dennett would argue. But sure. I do think that there is a fundamental difference in kind between the kind of agency we have, because I'm an emergentist. We're embodied in the physical world, and you get all of these. I'm a big fan of the free energy principle by Carl Friston. So you get these like emergence of self-organization and information. Sharing across scales and so on, and we're kind of like embedded in this very complex physical dynamical system, and that gives rise to a lot of the function and dynamics and behavior, which you could argue that the agency is a very real way to partition that system, or you could just argue that it's a mode of cognition. Sure. But you certainly could argue that there's a difference in kind between that dynamical system and the kind of thing that's happening in an LLM, simply because clearly, just if you look at the causal factorization of the system, we are using LLMs as tools. They are not the cause of their own actions.
Yeah, so I mean, it's going to depend on the system, right? So you can also use humans as tools. Like I can also have a warehouse full of humans, and I can say, please solve task X. I can give them the exact same prompt I would give an LLM. Like you can have you heard of Mechanical Turk? Like you can in fact, I can write a prompt for my LLM. I can give it to an LLM. I can give it to a human. Results look similar to me, right? So there's a sense in which humans can also be used as tools in the same sense that LLMs can be used as tools. Now, that said, it is the case that like, and then people can, try to construct agents, I would say both out of LLMs and using LLMs. So like in some sense, like the way people typically construct agents is via like a combined system of a LLM trained with RL and scaffolding around that system, which prompts it and, tells it what it should do. I would say that from my perspective, the scaffolding, it's more invasive than how you would get a human to do agency. So like people typically don't have, they don't build scaffolds around their human employees. But it's also like, I'm just like, humans do benefit from this stuff. Like if you want to get a human to be more agentic, and in fact, humans are not arbitrarily agentic. They sometimes sort of just do the same old thing and don't really think about what they're doing. You use things like you give them checklists. You periodically are like, hey, are you making a mistake? Like, and like there's this, quote, this anecdote I love from Meter, which is an organization that works on assessing model capabilities, and part of their work is in constructing AI agents to answer the question of like how good are LLMs at agency, which is that they found that very often, at least for earlier models, it was very helpful to ask the model, "Are you confused?" And they would just periodically ask the model throughout its reasoning, "Are you confused?" And the model would be like, "Oh, I was confused. What a good point." And then it would fix itself. And I think this works for humans too. Like I think for humans, you'll often end up in a regime where you're sort of doing the same thing on habit, and you need a reminder from the outside that you can do that. And of course, it's possible for humans to generate the reminder. It's also possible for LLMs to generate the reminders. You can train LLMs, or you can produce an LLM system that ultimately knows that it should check that it's confused. At least in principle, you could produce such a system. Now in practice, what's going on is that LLMs are really dumb. And so like my guess is what's going on is basically like people try to construct agents out of LLMs. They're quite dumb. They're also, trained in a very different way than humans. They kind of suck at agency. And so you end up with a system that does like kind of derpy, does a little bit of agency. It's got too high of a failure rate. It ends up falling on its face all the time, but it can get some stuff done, right? Like you can, in fact, have a system consisting of, let's say, like 3.5 Sonnet that goes around and it's like, oh, how should I start? And it thinks of a plan, then executes that plan. It proceeds with that plan. It runs into obstacles with the plan. It revises the plan. It notices that the thing it tried that it thought would work didn't work based on outcomes from the world. Like it runs the code has an error. It looks into the error. It realizes the error doesn't work. It puts in some debugging into the code to figure that out. And like the thing I'm describing is like, it's like the thing working better than it typically does, right? Like I think the more typical case for a lot of hard cases is the model just falls on its face. But I'm like, sometimes the models, they go for it, they keep going, the loop continues, they proceed. And I would say in this case, it really feels to me like the agency is actually coming from the model itself. To a high extent, like you gave it advice, like you gave it a prompt that tells it how it should do that, and you gave it access to tools. But I would say it's very similar to the human case, right? So like when we train humans to like follow processes. Like when I was learning to write software, I both learned via an iterative process where I tried stuff and things didn't work, and then I learned a process. But I also learned by pairing with other humans and imitating those humans and imitating how they learned to do agency. And like agency is a learned skill. You can learn the question, like you can learn the answer to the question of like, when should you stop and reconsider what you're doing? When should you like give up on your current plan and think of a new plan? Like, how should you select what are good plans? Like, what are the properties of good plans? All this stuff, I think is there. And so I guess I'm just like, my view is much more like there's not this hard boundary of no agent versus agent. There's some continuous thing of like, how good is it at agentic tasks? How good is it understanding its situation, acting coherently on the basis of that, acting plans, thinking of plans, like putting together things over the long run, recovering from its mistakes, just all these abilities. And models are getting better at them over time. If you looked at GPT-3, you would not be impressed. Like, if you looked at the models that we had 4 years ago, you would not be impressed by how they worked as agents. They didn't work as agents at all. If you looked at GPT 3.5, you would not be impressed. Like, that model cannot do agency at all. It can't understand its prompt. It doesn't understand how to use tools. But then you look at GPT-4, I don't know, there's a big jump. Like, it's much better at looking at tools. Or at using tools. It's much better at a lot of this stuff. And I'm like, well, things are progressing rapidly. Like, if you looked at an otter, I'm like, if you had an otter and you give it access to all these tools, you tell it what to do, I'm like, it's going to fall on its face. It's not going to program any software. And I'm like, it's got a combination of it wasn't trained to write code. Like the otter's upbringing wasn't very useful for this, which is true for the LLMs. The LLM's upbringing wasn't very good for agentic tasks, but it's also the case that the otter is kind of dumb. It's an otter. It's going to struggle to understand what's going on. And I think I'm just like, the situation feels much more like we have like a system that's like kind of just like it's very dumb, but it's got some stuff going on. It's very weak. And like the models are getting better. And I also wouldn't index too hard on current architectures. Things are evolving, architectures will change. Insofar as agency is really useful, I don't know if you're familiar with this, but Gwern has this essay, which I think it's old, it's an oldie but a goodie, which is like I think it's like AIs want to be agents, not tools. I might be messing up the name there, but it's something like this, and it's like, well, people are going to want to make their AIs into agents. And it's just very natural, and people are in fact already doing this. Like, it's very natural that I want to be like, hey, can you solve this task? And I want the model to go out. I want it to try stuff. I want it to interact with the world. I want it to notice its failures. I want it to learn things. I want it to improve over time. I want it to take active actions that I didn't explicitly instruct it to do. That's just going to make it much more useful. Like when you employ humans, you don't want them to just sit, do exactly what you say and nothing else. You want them to really pursue things. And I think there's just going to be a natural evolution where AIs become more agentic, more situationally aware. People train them in this direction over time. Yeah, sorry, it's somewhat of a long response, but...
No, I mean, I agree with a lot of that. I mean, first of all, I'm not a human chauvinist, and I agree with you that there is a spectrum of agential dynamics in a potential system that we might build, right? And if you think about it, the spectrum goes from, actual, 10 out of 10 agency all the way to sort of like just autonomy or automaticity, where the things are just kind of impulse response machines on the other end of the spectrum.
Yes.
I agree with a lot of what you were saying about, this reflection and deliberation is very important. But a lot of it as well, it goes to when I spoke with Kenneth Stanley, he's got this research about open-endedness, and he wrote this great book, Why Greatness Cannot Be Planned. And when I interviewed him, I realized he was basically talking about agency, and he was saying that a really good system is a system that has diversity preservation and it accumulates information all the time. And when you set up agential frameworks in LLMs, they kind of mode collapse and they converge. They stop accumulating information. They just kind of become sclerotic, and you can try and counteract this by, let's say you might have a controller, an external controller, where you constantly say, are you sure? Are you sure about this? Have you thought about this? Or you could actually set up a multi-agent system, and that will increase, diversity preservation and divergence as well. So the agents can be saying to each other, are you sure about this? Why don't you think about this? Why don't you do this? But LLMs, though, still have a fundamental limitation in the sense that they are basically just a statistical representation of their training set. The way that they're trained and the inductive priors and so on, forces them to focus on the high frequency attributes. So like a lot of the kind of the low probability long tail just gets kind of snipped off. And that's why when I use GPT, it just tends to just not want to give me more verbosity and more information. It always wants to give me the simple thing. It always wants to give me the boilerplate thing. Now, you can try really hard. You can be super specific. You can say, no, I really want this thing. I want you to do this and this and this, and please, please, please give it to me. That I'm the driving force of that. So I guess what I'm saying is, yeah, I agree that we could go quite far on that spectrum of agentic dynamics, but the only reason why it's different for us is because we live in the very complex physical world. There's just so many like sources of data generation, and we're doing active inference. So we're actually updating our weights, and like us as agents are kind of diverging and then sharing information and then diverging. And it feels like a difference in kind to me.
Yeah, so let me respond to a few things. So I think you made a bunch of specific falsifiable empirical claims, or like
Okay.
maybe somewhat vague, but they're empirical claims and they're falsifiable. And honestly, I think a bunch of them maybe are already been falsified, or like I mean, it's going to be a matter of degree, but they seem at least somewhat false to me. So you were saying that models only give you a boilerplate response.
Hmm.
I think you should think of this as a result of the exact RLHF process that was applied and potentially some limitations of that, and not necessarily something that's very fundamental to the system. So like, I think the reason why at least like, ChatGPT has a strong bias towards giving you the boilerplate response is because a combination of like, that's what worked best for it to get human approval in the RLHF process. And this is both because it's kind of dumb. And so kind of keeping it simple is the best approach for it. It's not that good. And also because like, it's just like they wasn't really rewarded for doing the thing you want. And I think in practice, if you were to start with a model that had higher entropy and then RLHF it to your exact desires, I think you would actually be much more impressed potentially. Another claim you made was you claimed that models are just a result of their training processes. They're just a statistical approximation of their training processes. I think I have a hard time operationalizing this in a way that doesn't either seem vacuous or false. Though it's an empirical claim, and we're not, it's somewhat tricky to adjudicate. But I'm like, well, humans, I don't know. They're also a statistical function of their training process. They're running some like statistical learning algorithm. They're doing some update, like there's some internal update rule. I don't know if you're familiar with like predictive processing, but there's some internal operation where it's like internal parts of you and like parts of your brain are learning to predict the results of other parts of your brain or predict the results of their own cognition potentially. I don't know. Sorry, I'm sorry if I butchered predictive processing for those who are more familiar. But I'm like, I don't know. It sounds very similar to what the language models are doing in some ways. And then I think there are limitations, but I would say the fundamental limitation from my perspective is in terms of depth, not in terms of the exact training algorithm necessarily is well described as producing a statistical approximation of the training data. So just because the training objective for a high fraction of training is predict the next word does not mean that the resulting system does not inside of itself do computation that is is generalizable and it involves like actually doing thinking. For example, as I was saying with predictive processing, it seems like a large part of human cognition is about predicting things, and it's just ongoingly predicting various other parts of the system. And I'm like, well, and predicting the outside world also, to be clear. And I'm like, it just turns out that's a really rich way to do learning because there's a lot of interesting dynamics in the world that you want to model. And a large part of being smart is understanding the dynamics in the world and being able to predict the dynamics in the world and having like a simple model of the dynamics in the world you can manipulate. Now, I should say LLMs are very limited on depth. So a limitation that they have is, unlike humans, at runtime, an LLM has only so much depth that they can still do operations in that depth. So they have activations. They are doing manipulation on that activations. I think this is pretty analogous to human learning within a short time frame. So humans can do a bit of learning over the course of a minute or two, and that learning is, I think, from my understanding of neuroscience, qualitatively different than the learning they do for longer durations. And I think so what's going on inside an LLM is you have many layers. Those layers are manipulating activations, potentially editing the activations, like refining the activations, adding knowledge to the activations, and any of these things potentially. We don't know exactly. In the human brain, my guess is there's something that's well described as activations, or is very analogous to activations. The human brain over the course of a minute is sort of manipulating these activations, storing the activations, representing the activations, evolving the state. And my guess is that human learning within a few minutes looks actually very similar to LLM learning within a few minutes in some ways. I mean, obviously it's architecturally very different, but I think they're going to have a lot of correspondence. And it seems to me like it's well described as learning. Like there's something going on where it's like those activations are being updated over time to better understand the text in the input or whatever output you have in the input. So I think I'm like,
Yeah.
you were saying the active inference thing. I'm like, well, it seems like to me like the internals of the model are actually doing something that's sort of like shitty active inference or like low dimensional active inference, and they've got limitations. They have a limited residual stream. They have a few numbers of layers, so they can't really do arbitrary things. But I don't know. There's some stuff going on there.
Well, we're not a million miles away from each other, to be honest. I mean, like, going to the extremely philosophical, you could make the argument of functionalism and computationalism, and that there are many ways to represent intelligent behavior in many different substrates and many different forms and so on. And we largely agree on that. I think it's just a matter of complexity and efficiency. So I agree that if you had like a potentially infinite size LLM and all of the training data and all of the compute in the world, then you could probably create a simulacrum of this type of cognition, But for me, I'm a big fan of the externalist tradition in cognitive science. So, I think a lot of cognition is external and embedded and embodied. And, there are many effective cognizing elements. I also think intelligence is physical. And again, I'm not making any like grandiose statements. I think for me, it's just a matter of complexity. I think, it really helps that we're embedded in the physical world, because that's where a lot of the effective intelligence happens. And that's the main reason why I think, even though there's no reason in principle why it couldn't happen in a large language model, it's just we have a lot more, universe compute power, if you like, in the real world.
Yeah. So one thing that's worth noting is it is the case that people who are blind, deaf, and have a poor sense of touch can, in fact, they can do stuff. They can learn to write code. Yeah. They can learn to operate in the world. And yeah, they're maybe less efficient in some ways. They have trouble learning some types of things. But I'm like, it feels to me like no specific sensory limitation feels that fundamental to me. And my guess is that, in fact, if you took a baby and you put them in some environment, I mean, this is a cruel experiment, so you shouldn't run it, but if you put them in some environment where they basically experience things in kind of a analogous way to an LLM, but in ways that provide for their basic emotional needs, they don't become, it's not the experiment works at all. My guess is that they would learn, and they would in fact learn to speak language. And also, LLMs nowadays, they're multimodal. They can in fact do that. So the main limiting factor on LLM training from my perspective is that throughout that training, they're not interacting with the world really. So they're sort of, they never produce, during their training, they just sort of see some input and predict the next token in the sequence, or do some predictive objective. As part of this, they never do something like learn on the basis of their own interactions, interacting with some complex system, as you were noting. But towards the end of training, they do. So people do RL. You can do RL in all kinds of environments. People have done RL, not on the basis of any private knowledge. They were just like, people do RL and on math, people do RL on all kinds of tasks. And RL does make the models better. Like if you train the model to learn how to interact with its own outputs, recover from its own mistakes, process the world in that way, it helps. And currently, this is a small part of training. I think all the arguments you've been saying so far are good arguments that are good arguments to think that you're going to need a bunch of RL. And my guess is that, in fact, it's pretty likely that you need a bunch of RL. And I think that, in fact, it's pretty likely that you get agency downstream of this RL. And I can imagine a world where you have LMs, you scale them up, you get something going there. But ultimately, it's not the most efficient way to do things. You would have to scale too far to get real power. So, okay, well, let's crank up the RL. People are probably starting to do this. I think it's a very natural next step if you have the systems that can do these things. People have been talking about post-training and post-training improvements. And I think you'll just continue to see notable improvements downstream of this. Like, it seems like GPT-4, there's been GPT-4, GPT-4 Turbo, a bunch of releases. Those releases have been the same price, but have been somewhat more performant on a bunch of tasks. My guess, just on the basis of speculation, is that this is downstream of improvements in RL, and they've been doing more RL. And so I agree in some sense, the current systems, they're weak, they're barely showing it, they haven't been RL'd that much, they're not that good at this stuff. But I think it's important to note that, like, these things are a continuum, they will be evolving, and you shouldn't be caught flat-footed. Like, things change fast. Like, things were very different 4 years ago, things will be very different 4 years from now. My guess is that, in fact, LLMs will not scale to artificial general intelligence will not scale to AI that can automate R&D and radically speed up human production in the next 4 years. Probably not. I think there's some chance though, and I think that chance is just like, well, I don't know, man. There's a lot of stuff going on. I'm uncertain. GPT-4, it's pretty impressive. GPT-5 could be pretty impressive. Who knows? Anyway, yeah.
Yeah. Well, I mean, there's a chance that GPT-5 won't be impressive, and maybe
I agree.
You'll update on that. But
big update for sure.
Yeah, I mean, I agree in principle with a lot of stuff you're saying. I think it's just the in practice part that maybe we slightly disagree on. And all of the stuff you're saying, very very true. I'm a big fan of the predictive brain and the Bayesian brain and the planning as inference stuff from Friston. Of course, there is a dichotomy between intelligence and representation inside our brains versus what happens outside of our brains. And also I agree with what you're saying. Yeah, deaf and blind people, they can do cognition, and of course that's because we're a collective intelligence. There's a whole group of us who do have multimodal cognition. I think, was it Einstein who was like sat on a pond and didn't he like throw a pebble in the pond or something, and that embodied physical experience gave him the abstraction to figure out relativity or whatever. I might be butchering that, but you see what I mean.
Yep.
Some of us can figure things out and then we can share it mimetically. We've got this beautiful language. It all works very very well together. But anyway, just coming back to this very interesting thing you're talking about, because you're kind of saying, well, we've got RL and we've got LLMs and we train them with a reward or with perplexity. And do you remember that Simulators article by Janice
I'm
on
familiar.
Less Wrong? Yeah,
Not
so
a
that
huge
was
fan of it, honestly, but
oh well,
I think
I'd love your take on that because I'm
Yeah.
doing that as an intro for my Murray Shanahan interview. But anyway, it's a
Okay.
similar thing to your Less Wrong article, which was about model intentionality and the model subverting them. But anyway, like in RL and in LLMs. And Janice made this argument that there's a potential divergence from the training objective and this kind of like intentionality, if you like, which is seen as an emergent property. And this is something that I'm skeptical because I think that it's an intentional stance. It's an as-if property. It doesn't actually have that property, but it's a form of anthropomorphization, and that's my main argument.
As in, your main argument is that so one view you could have is like AIs trained on prediction tasks will never in and of themselves have intentions. Of course, they might be able to, predict or simulate, as it may be, agents with intentions, and they might be able to be quickly and easily trained into agents with intentions, but the predictive thing. Now, there's a stronger view you could have, which is actually, if most of the training is prediction, and you don't have a big chunk of really powerful RL, you won't get intentions. But these are importantly different views. And right now we're in an intermediate regime we're in like a regime where we have mostly predictive pre-training, and probably we have a small amount of RL based on, like, for example, what it seems like Llama is doing. You can imagine a different regime where you have much more RL. I think the human brain, probably a high fraction of the processing power is spent on things that are similar to prediction, but there's also a bunch of like things that are more analogous to RL. I would say that it's worth noting that, referencing the simulators post again, or something like this, if a prediction of an agent is an agent itself, if a sufficiently good prediction of an agent, it just is the agent in some sense. And now the question is sufficiently good, right? How good does it have to be? And I would say that probably the way that you're going to get in short timelines, or in a short amount of time, very powerful AI is via a mixture of, you start with something like, oh, the AI sort of learned to predict human cognition. It's trained on a huge amount of human cognition data. Really, in some sense, the juiciest data, if you want to learn to be an agent, is imitating human reasoning, human outputs, which are just, as you said, entities doing a huge amount of agentic work in the world. And then you now start with that as your initialization, and you do some RL on top, and this gets you a model that is able to basically, you sort of build an agent out of the agent prediction bits that were lying around, and now you have an agent. And I'm like, well, you have created the thing. And I agree that it's pretty likely that you have to get to truly astronomical scale to get an agent merely out of the prediction. You could in principle. You could in principle get an agent, which is like a prediction agent. Like you could have inside of your LLM is a little homunculus, to use sort of a caricature, that is like, oh, what should I think about in order to predict this token? And it's thinking inside of an internal cognitive workspace that developed organically out of the void. That's totally possible. There's nothing that, rules it out. The flops are flops. They can simulate whatever. But at the same time, I don't know, that probably something that's really well described is that takes a while to emerge. The models are too shallow, probably not happening. But you can get a thing that has a bunch of agent bits floating around. It has the is this a good goal bit? It has the what should you do next bit? It has the notice that you're confused bit. It learned to predict all the behavior for all these things. You then do RL. It sort of pieces it together. SGD sort of munges these components together, and you end up with an agent. And I'm like, I don't know. I'm like, there's a quantitative question, which is how much RL do you need? How much additional secret sauce do you need? Or does it just work? I think I have a broad distribution over this question. I definitely think my guess is probably you need more stuff than current models. I'd be at least 60%, 50% that more stuff is going to be needed, but also that more stuff could happen in research in the next few years. It might not be needed. I'm uncertain. Anyway, yeah, sorry, pushing back to you.
Yeah, well, no, I mean, I don't really disagree with you. I mean, like, all I'm saying is right now, the source of causality and agency is the human. So if you imagine like a kind of agential contour map of the universe,
yes,
you know, it's emanating from the humans. And in a way, it's almost tautological to say, like, yeah, we could build a simulation of the universe. Maybe we would exist in a simulation, and that would have agency because it would sufficiently represent all of the function, dynamics, and behavior of everything in the universe. And, you know, so that's an extreme example. There are probably many intermediate points on that spectrum where, like, if you implement, you know, enough functions at a, you know, high enough resolution that would have agency. Maybe if you scaled LLMs to a you know, ridiculously high point, it would have agency. We're only disagreeing on, like, you know, how far you had to scale for that to happen. So yeah, I think we agree on that. But maybe you should just talk about your less wrong paper, because you know you were talking about this, you know, the behavior of LLMs potentially to subvert what you tell them to do.
Yeah. Okay. But maybe I want to just like jump back a little point, because I think it might be worth like operationalizing more specific things where we can be like get some, like, you know, real clean disagreements insofar as they exist, which maybe they don't. I think a view I have is that I would say that there's like maybe about I don't know, 35% chance that we'll have in the next 10 years really powerful AI. And then when we look at that really powerful AI, we'll be like, that really powerful AI was like basically descended from the large language model paradigm. You know, maybe there's some other stuff sprinkled in. Maybe there's a bunch of stuff built on top of that. Maybe there's elements that I don't even know about in that regime. How do you feel about that prediction?
I disagree.
You disagree?
And,
okay.
Yeah, and mostly it's because as well of what we were saying with reasoning. You know, so to have the kind of reasoning that we need, this inventive reasoning, we need to have, you know, Turing machines. And Turing machines cannot be trained with stochastic gradient descent. So all we could do is create what you were kind of talking about a little bit in your paper, which is, you know, we can create this computational graph, and we can do reflection and prompting, and we can constrain it in lots of different ways. But it will bottleneck very, very quickly. There's a limit to how much we can build an autonomous system. What will happen is that as the source of agency in the real world, we will use these things as tools. And don't get me wrong, it's going to change our society dramatically beyond all recognition. Right? It's going to change our interface with reality. It's going to change how we communicate with each other. It's going to create all sorts of risks. I mean, I'm completely on board with that. But they are going to be essentially, like, you know, part of our mimetic information ecosystem. Yeah.
So one quick thing. Do you agree that if people could easily create highly agentic autonomous systems that would, for example, autonomously do R&D and do end-to-end projects, people would create such systems? Or like in the absence of specific reasons they don't, they would want to?
So are you saying the question is, would people want to create agential AI?
That's right.
Absolutely,
okay,
because
great,
it would be a huge military and economic advantage. And just to be absolutely clear, by the way, I'm arguing that agential AI is not possible, you know, in practice. And we probably agree morally and philosophically that if it were possible to create agential AI, and there's also this notion spoken about by folks in the XRISC community of recursively self-improving AI. I think that's not possible in principle, but even agentic AI that could, in principle, you know, do science and become the cause of all of the major, you know, events on the planet. Of course, I would be very worried about that. I just don't think it's possible.
Physically possible, or likely to emerge in the next 50 years?
Well, it's definitely possible in principle, as we agreed.
Yep.
I don't think it's practically possible. And then there's a separate question of if it's physically possible. And even that, I'm leaning towards no.
Yeah. So do you agree that so it seems like I have a brain. I'm an agentic AI. At least I like to think of myself as an agentic AI. I think if you took my brain and you made a computational simulation of that, which I think is possible. So like best estimates indicate something like maybe you need about 10 to the 15, 10 to the 20 flop to run my brain. It's who knows? We have a lot of uncertainty here. We don't know what dynamics are important to simulate, but that we have estimates that are something like that, maybe somewhat lower. I think that if you were able to scan my brain, you know, cut it into pieces, scanned it all up, ran it in a computer, from my perspective, I would run it in the computer and be like, hey, I'm an agentic AI. What are you talking about? I'm offended by your insinuation that I don't have that. Do you disagree with this view? Maybe your view is that's not going to be technically feasible.
I do disagree, and I think it all comes down to our different view of cognition. So I think I think it's fair to say that you think of brains, basically you believe in the concept of a pure intelligence, and you think intelligence is inside of us. I think that if you were to make a simulation, you should be actually making a simulation of the entire physical universe.
We could just give it. We can just give it a little robot body. Just. I don't feel super. My guess is we disagree, but I think this is maybe not an interesting disagreement. So let's just say I'm a little simulation, but I also get to control my robot body. The robot body is hooked up to my brain in the same way that humans can learn to control prosthetics. I have like little camera. The camera is hooked up to my optic nerve in some nice way. I really feel like I'm just a robot walking around. Feels very similar to my previous life, though. Of course, I'm now a little robot, somewhat different. What about now?
Yeah, your cognition would be dramatically degraded as a result of your reduced dexterity in interacting with the environment.
So your view is like Stephen Hawking has dramatically degraded cognition due to his like paralysis, for example.
If he was born that way, I think he would have, yeah. But
he learned.
This is kind of what. Oh yeah. So there's
Okay.
two things. So I think that a lot of the way that we do reasoning and cognition is a function of our social and physical embodiment.
Mm-hmm.
So I think that if you grew up physically and socially embodied, you would develop a lot of those mental faculties. But I also agree with your earlier statement that even in absence of that connectedness socially and physically, a lot of intelligence is shared mimetically. But the more important question is, we could have cyborgs that extend our collective intelligence. But the real important question is, what if we just created like a super intelligent, simulation of a thing? Would that be able to do science in the same way we do? No, because we do that collectively. As we were saying with System 2 reasoning, the inventive component of reasoning and creativity actually happens on the margins. Like you need to have a population of millions of people doing interesting, diverse things in different situations in order to actually discover interesting new knowledge.
I mean, I would say like each person is contributing a bit of knowledge, but I agree that you indeed do go much faster if instead of having one person, you have a million people, perhaps a million times faster, or maybe somewhat less than that due to diminishing returns. But I also agree that I benefit from interacting with a small cohort of peers, though I think that if you put me out in the desert with a computer, I think I would in fact get a bunch of intellectual work done. Perhaps less, but I would get work done. Yeah, I think we have a pretty fundamental disagreement on intelligence downstream of this, where I really think like I agree that you need interaction with the world to get stuff done. Otherwise, you're just floating in the void. I also think that simulation might be cheaper than you're imagining. So if you just extrapolate out compute trend lines, we will have a lot of compute, and it's actually not necessarily that expensive to do things like have AIs interacting entirely inside of extremely diverse, realistic video games, and the AIs are just walking around doing their AI thing. They learn for, millions of years of video game time and emerge into our world after that in robot bodies. I'm like, if I thought that was necessary, I would be much less, I would think that AI in the next few years is much less likely. I also encourage you to think about, given that you agree that if agentic AI was going to happen, that would be a really scary prospect. It seems worth being ready to update. Or from my perspective, given that I disagree, it seems worth keeping an eye out and being like, well, is it agentic yet? Is it agentic AI yet? And thinking about what the bar should be. Like I don't know what your bar should be. I have some sense of what my bar would be. But I think, for example, if it was the case that the AIs are autonomously doing novel research papers you're impressed by, that certainly crosses the bar. And there's no human involved. They just went off and did their own research paper. Then that would cross it. And I think I'm like, at that point, maybe we should get concerned. And hopefully we can both agree on that.
Yeah, we can. I think our bar is just a little bit different because actually, like, we can analogize agency and creativity and inventive reasoning. They're kind of the same thing in a sense, because you don't necessarily need to have that kind of like self-directed causation and deliberation. Like you could argue that if we actually had an artifact which was producing new creative abstract scientific knowledge in the way that we were, then for all intents and purposes it's as if it had agency anyway, because we could certainly run it in a way that made it do that. I'm just saying that right now I'm saying that for all practical purposes the only thing that could have agency is something which is physical, which is to say us.
Yeah, so to be clear though, it wasn't just right now, it was in the next 50 years, which is a much more diverse span of time. Like I agree that right now we do not have such systems. I do disagree that it would need to be physical. Maybe I'm both more optimistic that the world of text is a more rich world, though it's not super rich. And I also think that simulations are maybe better than you're imagining. I don't know how much we should harp on this point, but I just want to clarify that.
Yeah. Well, I think the physicality is a big part of how we do things like abductive reasoning, because the universe and the physical world, it gives us so many kind of reference points to interpolate between. Because it's in a sense, like you could argue, we are just doing collective interpolation, and the data set is the physical generating process of the real world. And I think that you would need to replicate that as well in order to produce a similar type of intelligence.
Yeah, so it sounds like there's a pretty natural empirical experiment, which is a bit expensive to run, which is, suppose you take software engineers doing hard agentic tasks we both agree that would cross our earlier stated bar, like they're doing research papers. We're going to put them in a sensory deprivation tank. We're going to give them just their laptop, just the laptop, which is, AIs will have access to laptops. They'll be computer using agents maybe, or they'll, be computer using some things. I don't know if we should call them agents. We'll give them access to VS Code. They'll be writing away in VS Code. We'll give them access to their keyboard. Nothing else. Sensory deprivation tank. Feed them through an IV. And there's a question of, okay, suppose you had such systems, they only interact through this media. Maybe they get to do video calls with their friends. Same way the AIs will be able to do video calls with their friends. They're multimodal these days. Though, does good work get produced? My guess would be their productivity is degraded, but not eliminated.
I don't know. I mean, if you did it en masse, I think there would be a very quick mode collapse in the effective cognition. And so also, it's the same thing as we said before, which is to say the reason why they've developed this cognitive framework is because they grew up embodied and embedded in the world.
So we have to do a more expensive experiment. We're going to put babies in sensory deprivation tanks. We're going to give them little laptop screens, which are the same views as that. They're going to grow up in the sensory deprivation tank with their IV. I'm sorry, it's a very, very costly experiment, but we had to do it. And then we come out. Do they end up producing good work? So that one we can't run, I'm afraid. The sensory deprivation tank experiment with the engineers we could maybe run. Yeah, I mean, okay. I think I just disagree pretty strongly about the nature of where intelligence has to come from and where to learn. Maybe my view is I'm more optimistic about human intelligence than you are, where I'm like, human intelligence could diversely adapt to a variety of environments. There's hidden complexity in all environments, like a Python interpreter is in some sense a very complex environment. A computer is a very complex environment. You can video call other people in their sensory deprivation tanks, talk to them in words. I just think I think that just like the world is rich in a variety of perspectives. It's also worth noting that, as you said, the things you've said so far are totally consistent with creating really powerful AI with robotic bodies. As in, we could just, from the start, train them as robots in the physical world and just give them the same senses as humans, get robotic bodies that are just the same as humans. They have a sense of touch. They have a sense of they can see, they have cameras, they can hear. We have the sensors for these things. Now, currently, as you noted earlier, our actuators, they're terrible. Robotics, it's a mess. It's not very good, but like it's improving over time. But I'm like, well, I would say clumsy humans that aren't very good at moving around, they still can do things, they don't seem totally impaired to me. And I would say if we could just train AIs physically in the physical world using the exact same setup. We can also do things like train them massively in parallel and connected ways. Like one way to compensate for the weaknesses of AIs is that you can train them on a huge number of different rollouts. You can have maybe millions of different robot bodies that are really the same AI that periodically gets synchronized. And that would help it learn and help it learn faster. And I'm like, this is plausible in the next 50 years. Computers are advancing, robots are advancing. It would be a very expensive project. And I'm not necessarily advising this project. I think this would be a scary project for the reasons we said earlier. But I guess I just think I'm like, if you believe in human intelligence, it really seems like the separator can't be that strong.
Yeah, no, I know where you're going with this, and I agree that what you've just said is plausible. And I think that there would be economic and, kind of computational and physical restrictions just to, scaling out a collective intelligence of robot armies to that point. But, what you're saying is plausible. I just think, and even then, it could be said that those things in principle could be thought to be agential, and they could in principle be thought to be sharing information, creating information, improvising new meaning, new semantics, creating new language, whether in our agential gravitational field, maybe they would start to create their own agential gravitational field. All of this is possible, but I think part of the X-risk argument, I don't want to talk about X-risk too much, but it's that this would be like a super, super slow process. right? If there are any problems, we're the masters of the physical world. If there were any problems, we would just get rid of the robots. Maybe the people who worry about this big takeoff scenario think that there would be a recursive self-improving intelligence.
Yeah, I would say the term I would use would basically be I would say explosive growth due to I forget what the term is, but Tom Davidson has a report on this that I think basically articulates this, which is basically if you have systems and those systems are capable of improving themselves or improving other versions of themselves, then what could happen is you have the cost drops over time. So first it cost X amount of money or used X amount of hardware to run these AIs. And then somewhat after, as they optimize things, it now costs X over 2. And then now that they cost X over 2, you can run twice as many. And so now they're making progress faster. And then those ones have the cost again. Now you have X over 4, and now they're making progress faster. And the loop repeats. I would say that we have seen this throughout human history. So the population of humans over time has followed a hyper exponential trajectory. It has not just been growing exponentially. The rate of growth has accelerated over time. And I would say also the rate that's true for economic production. So the rate at which new ideas are being created has been accelerating over time, as our previous ideas have helped us create new ideas. So the main mechanism by which this has happened, I would say, is increases in human population. So previously there were a tiny number of humans. At some point maybe there were even only a few hundred humans doing a bottleneck early in our evolutionary history. And then over time, the human population has grown. And as the human population has grown, we have been better at generating new ideas because there's more people to generate new ideas. And then those new ideas have made it so we can support a bigger population. So there's the Green Revolution. Now we could support a much bigger population. Earlier than that, there was agriculture. I think something basically analogous, though potentially much faster, will happen in the case of AIs, where what you'll see is you'll start with having AI systems which are basically able to make it cheaper to run themselves. So maybe they tweak some CUDA kernels, and the CUDA kernels are now faster. Maybe they develop a new architecture which runs a bit faster. And then that will mean that you can now run more of those systems or better systems potentially, though more is simpler to think about, similar to the human population case. And now there's this population of AI agents that's growing hyper exponentially because every time they produce improvements that double how many could run. And then once there are twice as many running, the rate of progress is faster and they proceed. Now this is an empirical claim, and it's dependent on various specific empirical contingencies. So for example, the question you have to ask yourself is, when you double the population of agents working on the problem, or double the amount, more simply, when you double the amount of work that's been put into a problem, do you get improvements that are sufficiently large, or does it sort of taper off? And it will eventually taper off. There are physical limits, but it might taper off very late. So I think a simple situation to imagine here is, I would imagine that for humans are in fact on a trajectory which will slowly reach advanced technology, and there'll be more humans and advanced technology, and you'd spread to space and you'd keep advancing, and that would actually go very far. And it would happen over hundreds of years, but it would proceed. And I think the same could be true for AIs, but potentially on a faster timescale for various reasons. Now, I think this would potentially require both advancing hardware and software in tandem. So the AIs would be working on, GPU R&D. The GPUs would be getting better and better. As the population of AIs gets bigger, they're getting better and better at advancing GPU R&D. The rate of GPU R&D is increasing, the population is increasing, and it goes off. I think recursive self-improvement is not an amazing word to describe this, because I imagine that the process is more like a whole economy of AI agents building up an economy that accelerates over time. And yeah, I don't know. I think this is quite plausible. And I indeed think this is a big source of the risk.
Yeah, I think many of the things you said there are plausible. I mean, I'd push back a little bit that you said that our scientific discovery is increasing exponentially. I think that there's a kind of ephemerality to it, or maybe a better way of describing it is, we're not discovering new areas. There's a convex hull of known knowledge, and what we're doing is we're spending more effort kind of exploring inside that hull. And actually, in doing so, it creates a kind of basin of attraction, and there are forces that are stopping us from discovering new, paradigmatically changing knowledge. I agree with what you said, that the Industrial Revolution and several other things in our history created a paradigmatic change in how we organize ourselves, and AI could be that thing. And also there could be other things, and it won't necessarily be the AIs that discover it. It could be us that could discover it, and it could happen at any time. But then I'm interested to kind of ask your opinion on, like we're getting a new government in the UK tomorrow. There's going to be a
Yep.
new prime minister coming in, and as far as I'm concerned, it doesn't make any difference because it's going to be all the same people working in the in the government doing the same thing, and there are all of these like externalities and like financial markets and blah blah blah, and they don't really have much control to change anything. And similarly, we can't really change climate change because we've got a whole collective of people following their own gradient of interest and so on. So even if this were the case, and there was some paradigmatic change in technology, I mean, seriously, what are we actually going to do about it?
Yeah, so you're saying, suppose it was the case that we will actually get powerful AIs. There will be some sort of feedback loop of the sort we were describing. That feedback loop will, I think the technical term is fume instead of fizzle. It will grow, it will, accelerate over time rather than decelerating. It'll be growing at a hyper exponential rate. What should happen? I obviously have a bunch of views on this. I think the number one thing that seems really important for a lot of people to be tracking is that we really need to know how good current AI systems are. We need transparency into the level of capability. And for this, I would say what we need are good benchmarks that a broad diversity of people agree that if these benchmarks indicated that the AIs or indicate like if the AIs cross this bar in the benchmarks, then now we'd potentially be getting close to the point where this is plausible, where the AIs could in fact accelerate AI R&D, accelerate R&D in a variety of domains by huge factors, like factors of 10. And then once that happens, I think that dramatic response from society is warranted. So minimally, I think the weights need to be secured. I think that algorithmic secrets become a matter of national importance to Western countries and become potentially a huge national security risk. I would say that algorithmic secrets are already a huge national security risk because this is likely to happen or has a reasonable chance of happening in the next few years. But you can take what you get, and I would say at least we can secure the weights and secure the algorithmic secrets once this is happening. And then from there, we're going to have these agentic AI systems. And we'll have some concerns. So these agentic AI systems, we might not understand how they reason. We might not understand how they work. They might have goals that we didn't put in them because they do have goals. They are accomplishing things over long time horizons. If these systems did have these goals, did have these things they were accomplishing over long time horizons, I think we want to be able to make a case that the situation is safe, a case that these systems will not autonomously on their own cause bad outcomes. Also a case that humans won't be able to misuse these systems, won't be able to steal these systems in ways that are catastrophic. And my current proposal for how we should do this sort of safety case, or as it might be, sufficient countermeasures to diffuse a risk case. There's some empirical questions about how you want to do this. The thing I would be excited about doing is arguing that our countermeasures are sufficient to prevent these AIs from causing bad outcomes, even if they try to cause bad outcomes. So in the case of human organizations, it's often the case that we'll have organizations where we're worried about spies or we're worried about, disgruntled ex-employees, and we need to be able to be confident that these employees won't cause huge problems even if they wanted to. This is sometimes called insider threat concerns. And I would say we should basically handle a large fraction of AI concerns as an insider threat concern. We should say these AIs, we want to make sure that we have countermeasures, we have monitoring, we have oversight, we have checks and balances sufficient such that even if all of the AIs all at once decided to coordinate against us, decided to work against humanity, decided to seek power on their own, we would be able to stop them. And we would be able to either catch it or prevent them from succeeding in some way. I'd start there.
I mean, if I was to decompose that, I would factorize it into preventing the creation of new power and managing existing power. So what I mean by that is if the AIs became agential and, even though limited as you kind of granted self-improving or whatever, how quickly would that happen? I think it would happen very slowly because, obviously we already know that intelligence is about making these jumps in abstraction space, and every single jump would require iteration in the physical world, and there'd be various economic constraints and so on. So I think that process would happen quite slowly, but you're obviously arguing that it would happen very quickly. But then the other point you were making was about the management and governance of existing power structures. And that's very, very similar because even now, if you wanted to create AI, it's almost as hard as making a bomb. Right now you need enriched plutonium or uranium. It's very expensive. It's very difficult to get hold of. So now you're going to need to have potentially billions of dollars on compute. So it's probably easier to build. Yeah, it's probably easier to build a nuclear bomb than it is to build the kind of agential AI system you're talking about. So in that sense, I think it's more interesting to pivot over to the governance problem, which is very similar now, right? So we have various actors or virtual agential bodies. There might be governments, there might be military organizations or whatever, and they have incredible power and agency, which is to say they have the ability to like shift world events and, you know, create devastating amounts of violence and so on. And that's why we have this kind of mutual controlling structure and governance and so on. So I guess I'm arguing that don't we already do this now?
Yeah. So the situation I'm talking about is just a natural extension of current systems, or like of current systems in some sense. So I think the main difference I'm talking about with what I think might be the default, I think that on the default trajectory, it's both pretty likely that there'll be insufficient security. It's pretty likely that when OpenAI creates extremely powerful models, those models will not be adequately secured. They will immediately be stolen by a large number, potentially maybe one, maybe many foreign adversaries, and therefore undermining the potential like lead that Western countries might have. And I agree that national security interests will potentially notice this and secure the weights. But I think it might be a time crunch. I think even if national security eventually wakes up to these concerns and eventually realizes this is a huge issue or notices this, it might be too late to ensure that the weights have not already been stolen or that the algorithmic secrets have not already been stolen. And it's going to be tricky to maneuver into a regime where the weights are secure. So that's one thing. The second thing is that normally human organizations do not assume that all employees working for them are misaligned, actively conspiring against them, and potentially willing to coordinate with other human employees to undermine them. So currently, human organizations work on a combination of goodwill, people having sort of, not being like super power seeking, people like, kind of wanting the mission of the company, not trying to actively undermine it and subvert it at all points. I think it's plausible that AI systems will have these wants and desires, though it's not obvious. I think it's unlikely, but plausible, and it's a concern worth worrying about. And I think that will actually pose substantially different risks. I think it's very different to run an organization where you have hundreds of millions of AI agents running at 10x speed, doing things you maybe don't understand by default, where they would, if they could, all coordinate against you to screw you over, versus running Google, where you have 100,000 human employees. You can potentially look at what they're doing. You kind of understand what they're doing. It's precedented. I think it's a much scarier situation. Beyond that, so far we've been talking about sort of maybe AIs that are not wildly different in their capabilities from humans. And these AIs, I think, can be like controlled in the way I described with behavioral countermeasures. I think it's very likely that after you have AIs, which are of this sort of human level, shortly afterward, due to accelerated AI R&D, you will have AIs that are much more powerful than that. You'll have AIs that are much smarter than humans, that are the equivalent of humans running for many, many years at 10,000x speed, or are equivalent to they're much more creative than humans. Minimally, you can imagine just like the best humans in any domain mashed together, all operating at once. Given your views, maybe you would imagine that human operating in a physical environment in some simulated world for a while before coming out with some ideas, though I think that's probably not necessary or not the most efficient thing. I think those systems pose even more risk because now they might be, by default, the most economically productive, the most militarily useful ways to use these systems will involve them doing actions that we don't understand. Like they'll be so far beyond us and their state of technology might advance so quickly that they'll now be doing things like autonomously building factories for devices we don't understand, which are much more powerful than our previous technology. And I don't know. I mean, that sounds really scary to me if that's happening. My guess is you agree it's scary and you just disagree about the probability that that's going to happen.
I do. I think we disagree about the trajectory of how this thing will evolve. So if you think about it, even if we did what you said, right? So we have this like army of robots that are, developing an agential contour map around them, if you like.
Sure.
I think about it like a Venn diagram. So the agency contour map develops very slowly over time. So initially there'll be tools. So all of the robots will be working for individual humans. Their utility and function will be for humans, and they'll be bottlenecked by sharing information to humans in a way that humans understand. And I agree over time that they could develop more and more agency and they can start sharing information with each other and so on. But this divergence will require so many iterations. Just being able to physically replicate themselves will require factories which are managed by humans, which we control and so on. So what you're talking about is possible in principle, but I'm just saying that the scale is much slower. The other thing I'm worried about, you were talking about like deception and like bad actors and what was the word you used earlier? Insider threat was the word you used earlier.
Yeah.
And all of this is true, but I also worry about this kind of move towards not only paternalism, but I've also also seen moral paternalism in the effective altruism and rationalist type communities, which is basically saying that, we can come up with this moral abstract framework, and this framework is the best way to kind of have a calculus about how the world works and predict things in the future, and we know better than you. And it's the same thing with the insider threat and the alignment in order to do effective governance. To me, it's quite worrying that it's a kind of centralization of power, and it's like a reduction of our human agency. And I find that almost more perniciously negative than I guess I'm saying like the cure is worse than the disease.
As in, you're saying that we should let the AI seize control if they so desire?
Well, no, I'm just saying that on the basis that agential AI could seize control, we're kind of advocating to enforce a very rigid a form of governance which erodes
I was just talking
agency.
about enforcing that on the AIs and also preventing the weights from being stolen. I wasn't proposing surveillance on humans.
Oh, sorry. I thought you were talking about insider threat and misaligned people. Yeah.
Yeah, so I think the thing I was saying was that we're worried that AIs might be misaligned. I was proposing applying the standard technologies of insider threat protection from human organizations to those AIs and using what I would call like control measures or making a control safety case, which would be like arguing that the AIs couldn't cause problems even if they wanted to. I also think that because AI companies will be basically, in the world I'm imagining, the most important companies in the world and the most important projects in the world, and will be basically critical defense contractors and critical infrastructure for national security, we should also be potentially taking aggressive measures to ensure that employees at these companies can't cause bad outcomes. But this is just standard for defense contractors. Like if you work at Raytheon or whatever, you can't. They want to make it so you can't steal the missile plans and send them abroad. And I'm not proposing necessarily any invasive surveillance on normal citizens. I do think that you'll need to do potentially compute governance, but I think the situation I'm imagining is more like make it so that no one can buy huge amounts of GPUs, so that we can not lose control over really powerful AIs insofar as that's possible. Or insofar as huge amounts of GPUs can make that possible. But I think I'm like, this will not be infringing on the liberties of typical people. If typical people are like, I don't think that the people should have, in the same way, I don't think people should necessarily have the right to buy enriched plutonium. I don't think people should necessarily have the right to buy 100,000 H100s.
So I didn't mean to misrepresent you. Then I think that's absolutely true. Because the other thing I wanted to pick up on is it's not just the code, right? So like, for example, if you're IBM now and your source code for whatever AI suite that, let's say they've got some big office suite and the source code got leaked on the internet. The executives at IBM would be very worried, but they needn't be, because no one's going to use that source code. It's impossible to use it. It's a similar thing with AI. So the source code that OpenAI use, I'm guessing, is actually quite simple. You could write an incredible AI system, probably in about 1,000 lines of code. The data and how they curate it and refine it is very important. But actually, it's about the operational knowledge and architecture and hardware and like the whole kind of supply chain around that. So I think like when you factor that whole thing in, and as you say, it is on the order of like maybe thousands or tens of thousands of H100s and so on. So even if another country did steal that code, it's not like they're going to be able to do anything with it, right?
Yeah, so first of all, I think the most concerning situation is not they steal the code, it's they steal the model. And they steal the inference code, and then maybe they don't use that inference code, they rewrite it. But like, I think you should be imagining the most concerning situation is you have this AI. This AI is capable of greatly accelerating AI R&D. It might lead to a dramatically different world in a few years, 5 years, 3 years, maybe even shorter. And it's also already massively accelerating defense technology, offense technology. It's capable of offensive cyber. It's capable of potentially making superhumanly powerful bioweapons via just huge amounts of cognitive labor. You have that system. That system is just, the weights are stolen. The inference code for it is stolen. It's now running on a Chinese server, inference or whatever, North Korean server maybe even. And inference is much cheaper than training. So it does not take many GPUs to do inference on a modern transformer. So for example, the biggest publicly known model is Llama 405B. That model, I think you can plausibly run it on 16 H100s, possibly fewer with aggressive quantization. 16 is not many. It will be easy to get 16 H100s. I think there's a question of how much work will you be able to do. So you won't be able to do that much inference with 16 H100s, but you'll be able to do some. I think if you have thousands of H100s, you might be able to do a lot of inference and really a lot of cognitive work. So based on the estimates for flops I gave earlier, you can run a human at real time on one H100. So that means, and I think current AIs are actually cheaper for inference than that. So I think if you have 10,000 H100s, you could potentially, with AI systems in the next few years, be running like, I think it would be perhaps like millions of years of cognitive work per year. And so you maybe have like millions of extremely smart humans that are incredibly knowledgeable, or like the equivalent of millions of very smart humans. I think that poses substantial risks. Like currently, stuff is partially bottlenecked on top ML engineers at OpenAI. Every year, OpenAI has better algorithmic improvements. They release better models on the basis of better algorithms. If you instead had AIs doing those algorithms, things could go very fast. There could be millions of them. It seems like a pretty concerning regime. I think things will be continuous, but could be very fast. Addressing another point, I think there are like multiple components you need to be worried about being stolen. So earlier you were saying there's the code is simple. I think I agree that in some sense the code is simple, but I think the code contains like a large number of insights that are important. So algorithms improve over time. So like if you were using 2017 algorithms, you just took the transformer architecture, you implemented it naively, you scaled it up, your results would be like a lot worse than what we get right now. So an organization called ARC-AI has done estimates of how much algorithms improve over time. Their estimates indicate that the improvement rate is somewhat below an order of magnitude every 2 years. So that's like, as in the amount of bang for your buck you get is increasing by a rate of about 3x or maybe 4x per year. Or yeah, probably closer to 3x per year. That's pretty fast. Like that means that in 2 years you might need 10x fewer GPUs. And so I think it's also a concern, which is like, well, initially when you really have powerful AIs, that AI will take a lot of GPUs to run. It will take a lot of even more ungodly quantity of GPUs to train, but that will be decreasing over time. We'll be in a somewhat race against time with these algorithmic improvements advancing. And then once systems are very cheap to run, it really becomes, or very cheap to train and very cheap to run, the governance problem becomes much harder. As you were noting before, if compute governance, like tracking the supply of computer chips, can be used to govern really powerful technology, that's great. And that will last for some period. Hopefully will last for a while, where we can have some handle on AI. We can have some control over AI via compute. But it will eventually fade as technology gets more powerful, would be my guess.
Yeah. I mean, one thing that does strike me, coming back to the ARC challenge for a little bit, one of these like big leaps forward could be that we figure out how to compress the amount of computation that we need to do, for a similar amount of intelligence. This is kind of what you're talking about, because, right now
Indeed.
we can agree that if we had like bazillions of compute power, then in principle we could do all of the things. But, that's still kind of like limited by economics and hardware and GPUs and so on. So maybe there'll be an invention, let's say something that we might discover on the ARC challenge, where we can actually do a significant amount more. There is already a trend actually to make smaller models. But I still think that there's a trade-off there, and the smaller models are doing less intelligence, a commensurate amount less intelligence. But just to comment on the other thing you said, my main, because I just want to make it clear to the audience that I do disagree with you on this point, that I still think you are thinking of human cognition or humans as islands, and you're kind of making a commensurate relationship in terms of the amount of computation that happens in a brain, and like we can reproduce that in a GPU, and then we could have 10,000 of them, and then we could have like blah blah, all of this kind of stuff.
Sure.
I disagree with that in principle, but we've already covered that earlier, so we don't need to go over that again.
Yep. Yeah. I mean, for what it's worth, the place where I expect the progress to come from is basically mostly at this point in large AI labs. Because maybe I'm more optimistic about the LLM paradigm than you seem to be. And I would note, so you said earlier that small models are just basically, there's something limited about them relative to bigger models. I want to push back on this a bit. So a while ago, NVIDIA trained a model called, I think, like Megatron NLG. So it's really, really big model, 540 billion parameters. It's actually bigger than the planned Llama 405 billion parameter model. My understanding is that model was actually worse than GPT-3, or at least comparable to GPT-3, and that people have made 7 billion, 10 billion parameter models now, which basically strictly dominate GPT-3. Like, it's very hard to find a task in which they're worse than GPT-3. And my understanding is basically that it is actually the case that you can make smaller models that strictly dominate historical larger models. And my guess is it will be the case that the current, recently Llama 370B was released. My guess is that according to the sort of trend lines I was saying earlier, in a few years, you'll be able to create a model that's 10x smaller, 10x cheaper to run, which is basically like as good as Llama 370B. I mean, this is an empirical claim. We can just look at this.
Yeah. I mean, on that, the way I think about it is part of the reason we over-parameterize deep learning models is to make them statistically tractable to train. So SGD works much better when you have more parameters, But when I think about what is the model actually doing, well, it's a bit like a zip file of the data set that you're training on. So what it does is it will kind of like learn a manifold for all of the data, but it does an expansion. It's more than a manifold. So you have like these inductive priors that do these in a self-attention transformer, it's doing a bunch of symmetry permutations. So it's kind of like as well as embedding the actual data that went in, it's embedding like lots of like arrangements of the tokens and so on. So you get this like big convex hole around the data distribution, and then there's the case of, okay, well, we can make these things more efficient, right? So they need to be trainable, but perhaps even after we train them, we can sparsify them, we can distill them, we can do a whole bunch of stuff. So there's presumably some kind of like information theoretic like optimum trade-off between I'm representing as much of that distribution as possible, and I can get down the compute, but surely there's a limit there, right?
Yeah. So getting on that, so there's scaling laws. So what people have found is there's a relationship. So suppose that you want to get as good of a model as possible, just like it's just as smart as possible, or smart as it may be, as performant as possible at the end of training. It turns out that you want to use basically as much data as you have parameters based on the last publicly known scaling laws, which are the chinchilla scaling laws, or like basically people do something similar. And so I would say, actually, in this regime, interestingly, models are in some sense not over-parameterized. So if you train a 7 billion parameter model on a number of tokens that is a multiple of the number of parameters. So people would normally train, the compute optimal amount to train a 7 billion parameter model is, I think, about 20x more than their parameters. So it'd be around 140 billion tokens. And so that's quite a large number of tokens. Now, in practice, you can do better by training on more data. And our scaling laws do indicate that this plateaus. So it turns out that if you train like a 7 billion parameter model with current methods on an infinite number of tokens, then based on the extrapolation from our scaling laws, I think it's the case that that model will never be better than Llama 370B, no matter how much you trained it, with the current architecture and current improvements. However, there are improvements other than that. Sorry, I might be getting the numbers wrong here. It might be that it's never better than like what Llama 405B would be, but like there is a limit here. So the functional form of these scaling laws is basically there's a data term and a parameter term, and you can basically reduce either term by increasing parameters or increasing data, and then you have to increase both at the same time to be compute efficient, and that gets you more performance. I definitely agree that there's, and also, sorry, to be clear, there's definitely going to be a limit somewhere, right? So even if the scaling laws indicate things scale forever, well, we only have so many orders of magnitude we've seen so far, things can fall. But we have seen a lot of orders of magnitude. So I think people have seen scaling laws over maybe like 6 or 7, maybe even slightly more orders of magnitude. I think extrapolating out another 6 or 7 orders of magnitude on the actual loss number is plausible. Now, we don't know how that loss number translates into downstream performance. Could do whatever. There might be limiting factors to scaling out that far, right? So eventually you run out of data. At some point, you're in a truly ungodly compute regime. But yeah, there's more to your question that I wasn't getting at there. But that's at least
well. I mean, I just wondered if you can comment as well about what you think first of all, when I spoke with Aidan Gomez at Cohere, he was saying that things like LLM Cicerina, it's almost like we are dumb, like the models are smarter than we realize, and we're the bottleneck. It's not like the language models are saturating. I mean, what's your take on that? What do you think is the likely, like we look at commercial models coming out and so on, what's going to happen?
Yeah, so I think I'm going to talk about a scenario that seems plausible to me and scary, but is maybe not it's not like all of the probability mess, which is LMs are getting better over the next few years. Various benchmarks start saturating. So basically, like currently we've had a bunch of other benchmarks saturate. MLU is saturated. Maybe we start seeing like models are performing pretty similarly to humans on SWE-bench. SWE-bench, it's a pretty diverse task. It's not the most diverse task. Soon after that, models start performing quite well on basically like hard agentic tasks that are like would take humans 8 hours and would be hard. Like, for example, ML engineering tasks like getting an inference server running on faulty hardware and getting high throughput. And that involves like doing things that are basically R&D, like doing things like, debugging things, improving the algorithms, writing novel kernels. And the LLMs are starting to do that. That ends up happening maybe under a faster timeline scenario, maybe in a few years, we start seeing those AIs. At the same point as that's taking off, AIs have been helping people inside of AI labs accelerate R&D. And now AI labs are running somewhat faster than they otherwise would have been. They're hiring aggressively. The industry is growing in market cap. And in addition to that, there's this new factor, which is that AIs are helping out internally. That starts accelerating. Soon you end up having AIs that have sped up the pace of R&D inside labs by maybe a factor of 3 via mechanisms like the AIs are basically acting like junior software engineers at the AI lab, where you say, hey, can you like go implement this, test it, debug it, make sure it's running, and then if the metrics are X, do Y, and the AI goes off and it does all that. And then over time, the level of state and understanding of these systems will evolve, and these systems will now have basically more understanding of the previous state of research, and the prompts you'll give them will be even more open-ended. So they'll be more like, please go and can you do some research on how to speed up this kernel? Go. And it'll just, know about all your stack. It'll just have that all already in its understanding and then proceed. And at this point, like you can get potentially pretty big speed up. So there can be human bottlenecks. But once you have fully autonomous systems, the human bottlenecks sort of disappear. And your remaining bottlenecks are just how much compute the systems have and how many of them you can run. And you'll potentially be able to run a truly enormous number. Just based on how current scaling laws work, it turns out basically you can, if you imagine that we've trained a system on 100 trillion tokens, you'll be able to run them at inference for also about 100 trillion tokens with roughly the same cost as you train them on. And that means that you'll now have this system that can do maybe what is the equivalent of 100 trillion seconds of human time, which is an insane amount of human time. And then you'll have that system, you'll do a bunch of R&D, that will result in more powerful systems, and then things will accelerate. Around this point, probably governments will get involved. Governments will notice what's going on. They'll be like, whoa, these systems, they can now accelerate defense technology. They can now contribute and do massive cyber offense campaigns like the likes of which the world has never seen because there have been personnel constraints before. Things are going very fast. Something needs to happen. And then something will happen. And now from here, the world can branch in many directions. The direction I would like to see, or the direction I would hope for, is we can keep these systems basically controlled. We can keep them so they can't take over the world if they wanted to. They can't seize power that we don't deliberately grant to them. We potentially try to better understand them. And then I think that once we have systems that are accelerating the pace of R&D by a factor of 10 or 30, we really should slow down. I think that's a very scary point to be at. And I think it's really important that we are very careful and slow about the advancements beyond that, especially advancements into a regime that we cannot control. And we should be careful about the advancements to that point. I think it's going to be very hard to coordinate to slow down prior to getting to that. I think it might be possible to slow down aggressively after that. And then maybe over the next 10 years. So this is 3 years in, AIs are 2xing R&D. 5 years in, AIs are 10xing R&D. Maybe 30xing R&D. And then they hopefully slow down, maybe slow down even before that. Have slow advancements over the next 10 years, figure out a lot of stuff, figure out how to better control and understand AI systems, ensure that the AI systems are aligned with our best intentions. And then at the end of that, we potentially build incredibly powerful systems. Technological advancement becomes, we basically unlock all technology or unlock a huge amount of technology. You can potentially do aggressive space colonization, and then all kinds of crazy stuff might happen.
Yeah. I mean, first of all, I welcome the views in the sense that, MLST is about diversity of thought, and we do talk to people who have completely different views. So obviously, just to make it clear to the audience, I personally don't agree with that, but you're a very intelligent guy, and I respect your viewpoint. And you did actually say in the notes that you think around 2036 that that's your median forecast for ML R&D automation.
That's right. To be clear, I was giving an aggressive scenario, which is a concerningly plausible but aggressive scenario. My median view is that things will take longer than that.
Yeah, I mean, I think I suspect that it's a little bit like there's the myth of the 10x software engineer, and how software engineering doesn't scale up very well because there are so many bottlenecks everywhere. And I've got to wait for John, to review my pull request before I can get any work done and stuff like that. That's why I intuit that there will be lots and lots of scaling bottlenecks to this, and I think a lot of your intuitions are based on the idea of pure internalized intelligence. So it's almost like in lieu or absence of those scaling bottlenecks.
Yeah, I mean, I think that's basically a fair caricature. I would say that it's worth noting these systems will be running experiments, interacting with the world, but I agree that I'm imagining a world in which the intelligence is in some sense internal to the system, the reasoning, the research. I think that's accurate. That effectively describes how I operate. Other people may be different. as far as bottlenecks, so there's a bunch of possible bottlenecks that could happen. So one thing is that scaling might stop before it reaches these systems due to data limitations or compute limitations, because basically there's not enough funding, or even just supply constraints on GPUs because there's not enough fabs. But supposing scaling does get to the point where the AIs can be as smart human like researchers. Now there's a separate question, which is, do you have bottlenecks due to difficulties parallelizing? So, it's hard to scale an organization. It's hard to hire a lot of people. I think there's a bunch of ways in which AIs might be relatively less bottlenecked in this way, though it's an open empirical question. So, for example, AIs will be able to share all the same state, have all the same weights. They'll be able to be trained to aggressively coordinate with each other. They'll potentially be able to use non-language interchange formats, though I prefer that we stuck with language. I think that's much safer and much better. I think that they will be able to basically be learning all this stuff in parallel. We'll be training them on a bunch of different things in parallel. In addition to this, even if it's the case that things are quite bottlenecked on personnel, it is still the case, quite bottlenecked on not being able to scale up to more personnel. Like, as in, you have millions of AIs, but you can really only productively get use out of 1,000, and beyond that, you have strong diminishing returns. There is still returns to intelligence. So imagine that your AIs are doing this, and you have 1,000 smart AIs, and next year you have 1,000 really smart AIs, and the next year you have 1,000 really, really, really smart AIs. You can still get advancement from not from huge scale, but instead from that. I would also say that in various ways, if you're running fast enough, I think a fast, dumber system can usually approximate a smarter system to at least some extent. So, for example, you can do things like sample a bunch of different possible approaches and pick which one is best. And now that this gets you some advancement. It's not going to get you an infinite advancement, but it gets you some improvement. And then there's just a question of how far does this sort of thing go?
Yeah, it's a little bit like your ARC solution.
Indeed.
Yeah, which is very, very similar. But I also think that, if it did roll out in the trajectory that you're talking about, I mean, there would be an intermediate massive disruption to the job market, and there would be a revolution, because people wouldn't be needed to do their jobs anymore, right? So in a sense, we almost don't need the whistleblowers further down the stream.
Yeah. So I think there's a few things that make me slightly more concerned than that is imagining. So one thing is that it's plausible to me, and I'm concerned about cases where the big AI project enters basically a top secret situation and has low transparency. I think that's very concerning, and I think we should try to ensure sufficient transparency that independent experts can basically understand what's going on, understand the systems well enough to know whether or not they're safe. You can have like a third-party auditing regime. The second thing is, it's not obvious to me, especially in these faster situations, that people will lose their jobs. So economic growth does not necessarily result in job loss, often involves some displacement and some new jobs. It's plausible to me that with things moving this fast, employment will be kind of sticky. So people will be reluctant. Suppose your business is booming. I think typically you don't want to fire people when your business is booming, even if there are not huge returns to the personnel you have. And you might want to keep them around, try to shuffle them. So I think it's not obvious you'll get a labor market disruption. My guess is you probably will under even faster situations. But like I think it's like an open empirical question. I'm not an economist. I think things can be sticky. I wouldn't make strong assumptions here. Now, I agree that there'll be a lot of disruption in the world from other things than jobs. So, for example, I think it'll be clear if these systems are deployed that they're very powerful. I think that people will potentially have, AI girlfriends, AI boyfriends. People will be like, what are the kids up to these days, And I think that it will be clear that some change is going on. I think I both worry that society will not respond early enough, and I also worry that society will respond in the wrong ways. So I think that there's some interventions that will be actively counterproductive, and I think there are some interventions that will be very helpful. And I think both these interventions are on the part of governments, on the part of civil society, on the part of academia, and on the part of AI labs. And I think getting it right is going to be, if the scenario I'm outlining is right, I think it's going to be really important to get this right, because this will be potentially the largest, most important event over the last several hundred years, possibly for all of human history.
Very interesting. Well, Ryan, we're nearly at time, and this has been an amazing conversation. But could you just finish by reflecting on, the ARC challenge? Like maybe what do you think is going to be the best solution? What do you think is going to happen there? And any final reflections on your particular solution?
Yeah, my guess is that the frontier of like ARC solutions will be basically based on taking large language models that are on the best language models at the time, probably large multimodal language models, putting some tooling and scaffolding, giving them access to various tools, maybe doing something like running code, but if not that, maybe just at least giving them various ways to visualize things and having that be interactive with them. Taking those systems, using like a lot of runtime compute, because I think with ARC-AGI, it's very easy to leverage runtime compute relative to other cases, and then proceeding with that. That's my guess for what the frontier is going to be. I think, GPT-5 is supposed to come out maybe some chance before end of the year, pretty good chance before end of next year, probably it'll be multimodal. I think it's very likely that system will do much better on this task. And via the mechanism of actually like being like smarter in some real sense. I think, 3.5 Sonnet, recently released by Anthropic, seems to perform better. My original solution used GPT4o for various reasons. For one, Sonnet wasn't released at the time I was writing it. And that does seem to notably improve, at least in some cases, over 4.0. And I expect that will push the frontier there. Now, in parallel, there's my basic guess is that most of the progress will be driven by basically like expensive solutions using large language models. And that's what's going to happen. I think there'll be also a bunch of cleverness. And I think that at each point, you'll be able to basically compensate for the weaknesses of your language model by sort of putting in some cleverness, making sure that they're prompted right, making sure that they're that. But over time, the cleverness will become relatively less important compared to scaling. And I also think runtime compute will stay big.
Yeah, I wanted to comment on something because you said something very interesting a few minutes ago, which was that, it's possible for a kind of dumber system at scale to approximate a smarter system. Yeah. And I actually think that could happen when we have, like societal collective use of LLMs which do active inference. So, for example, the reason why Francois Chollet fastidiously guards the data, because he knows that the knowledge gap and the fact that the data is hidden is the only reason why the LLMs can't do it, right? But just imagine that if this was unleashed in society and lots of humans were doing the system too, and they solved the problems, and then like we did the active inference and we just kind of put the as Jack Cole does, basically do the active inference and then put the knowledge back into the LLM. Then at that point the LLM could do the ARC challenge. And then you can just roll that out to what Chollet calls developer-aware generalization. So when human agents discover new problems, they'll figure it out, and then the data will go back into the nexus of LLMs. And then essentially we've got this functioning collective intelligence, which is an interaction of humans doing the system too and LLMs kind of representing it. So you could argue, well, what's the point? I mean, if that's just going to do everything we need, then why do we need to have this kind of special type of system two reasoning inside the AI?
Yeah, so earlier we were talking about accelerating ML R&D, and we were talking about bottlenecks. I think if humans are in the loop, that will indeed be a huge bottleneck. So when I have my collaborator do some project, and I'm like, hey, can you do this? Like maybe something like that. I don't spend my time watching his every move and being like, nope. I don't constantly point out ways in which he should do it differently. And in fact, if I were to do that, I would probably be oftentimes faster to just do it myself. And also I just would get way less speed up. And I think this will be true for AIs. I think it will be the case that having like currently various occupations and various domains are limited by personnel, limited by amount of cognitive labor. I think that the more that the AIs are autonomous, the less this will be limiting. And so I think people will optimize strongly for systems that can run autonomously, that can correct their own mistakes. It's also worth noting that I think the systems will advance beyond human level intelligence in system two reasoning. And then at that point, it will look particularly weak to use the systems for that. I agree with I should note that I agree with a view in which probably the systems that will first be doing all of this will be using basically all the tricks in the book. So there'll be humans doing subparts. There'll be trained online, they'll be constantly being trained, they'll be RL ongoing, they'll be using whatever the best way to represent knowledge for those systems are. It'll just be all mixed up. It'll just have all these things going at the same time. Just because whatever the first system that gets there will be using a lot of tricks. I mean, I don't know exactly what the tricks will be, but my guess is there'll be a lot of tricks. But over time, I think the main driver will basically just be general intelligence of the core system. Probably it's not super obvious this is true, but that's my default guess.
But humans have this fascinating kind of juxtaposition of both autonomy and consensus. So part of the way that we improvise meaning, the way we discover knowledge, not only is it grounded in the world, but it's also grounded in our kind of culture and society and so on. So we're trying things out, and then we're sharing information, and the whole thing is kind of spreading out. Why would it not be the same for AIs? Like, why would they not argue with each other and have disagreements and just get caught up in knots?
Oh yeah, I'm not saying that won't happen. I'm just saying that it might look a lot more like first AIs are introduced into human society as sort of like a slightly strange like engineer, but they're like sort of a new sort of type of like or engineer or scientist or whatever. They're sort of a new type of cognitive labor with somewhat different properties. Like they're dumber, they're faster, they're whatever. They're better at some types of tasks than others. And then over time, these systems will become more autonomous. I think that it could look like a society of AIs existing autonomously. I think over time, probably if you just let things go as fast as possible, the AI society will diverge from human society. They'll talk to each other in different ways. We won't understand what they're doing. They'll be referencing research papers that were written so soon ago that and so quickly that we don't know what they are, built on top of a body of work done in the last year that we don't understand. And I'm like, at that point, like, yeah, there'll be AI society. I think it will be. It's not obvious to me how much it will go into like a huge number of small systems communicating versus a smaller number of centralized, like highly coordinating systems. I think it could go either way. I think there's downsides to synchronization, there's upsides to synchronization, but I think it will diverge from the human sort of memeplex.
Yeah.
I should note though also AIs have coordination tools that are very different from human coordination tools potentially. So for example, you can merge the weights of different AIs, you can exchange activations, they can all be the same weights trained using SGD. Like you can synchronize gradient updates. Gradient updates can be additive. So I think it's like AI society could potentially be very different from human society. It's possible that AI society is much, much, much more closely linked. Like it's much more like a bunch of like humans linked up with their brains connected with high bandwidth connections than our current society where I like laboriously write a Google Doc and then send it to my colleague who writes some comments. Like it might be very different than that.
Yeah, but it does outline, I think, like two of the issues I have. I mean, we've already spoken about this concept of a pure intelligence where they are islands and they can be in a, catacomb, like a, what do you call that?
Sensory deprivation tank.
So, yeah, sensory deprivation tank. But the other thing is this notion of rationality, because I was kind of teased that out. I was trying to tease that out with my question that there's a lot of subjectivity when we're doing epistemic foraging, and also for intelligence as a system to work well, there needs to be diversity, preservation, and divergence, and you need to have, people with different views and so on. So surely the AIs would also have different views, and that would actually be a good thing. And I think that the framing that gives you the opposite intuition, and a lot of rationalists and EAs and stuff have this as well. They think that there is an objective, like rational way to do things, and that the AIs would kind of hone in and ground on that, and this subjectivity bottleneck wouldn't be a problem.
Yeah, so I think I agree with parts of what you're saying, and I also agree with parts of the there is a right way to do things to some extent. So it's worth noting that you can have one system that represents a bunch of viewpoints simultaneously. So you can potentially be like, I entertain a bunch of hypotheses at the same time. And now humans empirically have a bunch of cognitive biases and have a bunch of limitations. So for me, at least, it's often a much better cognitive move to really focus in on one hypothesis and really think hard about that hypothesis and sort of do this one at a time. But it's not obvious that other systems have to have this property, right? It's not obvious as the best way to organize things. It could be, it could not be. Second of all, I think that there's a sense in which we want to have a bunch of different hypotheses floating around, but I think there can be, and I agree that we won't necessarily know what the right way to do that is. We won't know what the right way is to think about that. We won't at each point know what the exact right answer is. But it is the case that there are things that are dominated. There are dominated strategies, right? There are things you can do where it's clearly worse than some other strategy from some vantage point. And I think over time, things will become more and more efficient. So, for example, I think there have been a variety of sectors in which aggressive top-down optimization has radically improved efficiency. So for example, delivery truck drivers. My understanding is it used to be the case that you'd be like, okay, here are some packages, and you just let the delivery truck driver figure it out. Now there's aggressive tracking of everything. People are constantly doing A/B testing. There's automated routing to figure out exactly where to go. Every part of the system has been engineered, optimized, searched, learned, to the extent possible, because just shaving off 1% of cost is just hugely valuable. And my guess is that AI will trend in this direction. So right now we train AIs with reinforcement learning, and this will continue. And my guess is that will in fact select AIs for having cognitive patterns, having cognitive strategies that empirically perform better across a wide variety of circumstances. And you'll basically get systems that are smarter and smarter and better at various things as they get scaled up, as they, as algorithms improve. And so while I agree that there's no like foreseeable, obvious right way to do things, I think that there is like a space of like strategies that are better than some other strategies across a wide variety of situations. Like there's just like sometimes there are strategies that are better than other strategies in a wide variety of situations. So no free lunch means that they can't be better in all situations. But unfortunately, like the world has lots of there's no free lunch always, but there's lots of cheap lunch or whatever, right? Like humans have lots of heuristics that work across a wide variety of environments. Heuristics towards simplicity are good. Heuristics towards a bunch of things. AIs will learn these heuristics. They'll get smarter. And there's just a lot of headroom.
Ryan Greenblatt, it's been an absolute honor. Thank you very much for joining us today.
Yeah, thanks for having me.